Okay, I don't think I can hear you yet. Can we just try? One second. If anyone can put the speaker on.
Yes, we can hear you, ma'am.
Okay, I think you are speaking. I just can't hear it in my system. Okay, shall we try one more time? No. It's just... Yeah, I think it's just that my speaker isn't working, which is bad. Speakers. Okay, shall we try one more time, please?
Yes, we can hear you, but
No,
maybe
I
there is
still
problem
can't hear
from your
you.
side. Okay.
Okay, so I think we're just 4 minutes late, right? Shall I just try one more minute, please? Okay,
Yes, no
I'll
problem.
just dial back after test. Hello.
Hello.
Oh, now it works.
Yes.
Finally. Oh,
Okay,
God.
fine.
Oh, sorry, everyone, whoever is listening.
Okay.
Yes, I finally dialing back from my computer, so I just disconnected all the desktop and everything. So we are all good.
Okay.
So shall I just start sharing the screen, or?
Well, ma'am, I think we'll wait for some few minutes.
Okay, that's good.
So good afternoon, all the participants of this faculty development program. So this is the last day of the FDP. So I welcome you all to this session. So our first speaker in the last day is Dr. Sunit Purohit. She's a research scientist in the Green Metals Group of CSIRO Mineral Resources, specializing in low carbon iron and steel making. She's the inventor of the lime magnetite pellet process, a low temperature iron ore agglomeration technology capable of reducing blast furnace emission by up to 18%. So most recently, she secured $5.3 million in funding from ARENA, that is Australian Renewable Energy Agency, and is currently leading this project. Dr. Purohit has received several prestigious awards for her contribution to this field, including the Mission Innovation Net Zero Industry Award at COP28 and the CSIRO Science Achievement Award for Early Career Research. On behalf of the organizing committee, I welcome Dr. Purohit to this faculty development program, and she joins us all the way from Clayton, Australia. Thank you, Suniti, for accepting our request for this session. You can start.
Thank you so much. It's a
share your
pleasure. I
slides.
can see some, yeah, I can see some familiar faces. That's good.
Yes.
Not seeing you after a long time though. I'll just sharing my screen. I think you have to give me permission to share.
Yes. Okay. You can share.
Okay. Can you see the screen already or share? Okay.
No.
Yep.
Yeah, it's coming. Yes.
Yes.
Right,
Yes.
Yeah.
Yes.
Okay.
That's some like.
All right. So I think it's 2 p.m. in Indian time. So it's the afternoon nap time, I suppose. So my job basically is to make you all stay awake and don't let you sleep. I'll try my best. So it's obviously a pleasure to give a talk in the ATAL FDP program. This is my first time giving a talk for the faculty development program. I hope I can do the job. So the topic that I'm going to present today is in the recent advances in the decarbonization efforts that's going on in the steelmaking industry. So before diving into the topic, I'll just give you a brief about where I work. So I work at CSIRO, which is in Melbourne. And for the cricket fans who are attending the talk, you know it's the ground for MCG. We're just about 20 minutes drive from CSIRO. And CSIRO, before I go to CSIRO, let me just give a brief background of where I come from. I am basically from Odisha, IGIT Saran. I'm sure you can recognize me in this photo somewhere here. And IGIT used to look like this before. I'm not sure how it looks like now. I haven't been there for quite some time. And the bottom photo over here is the classroom. So there was a brave guy in our batch, I suppose. So he just went out, took that photo when we were doing the exam. So you can imagine how crazy we were at the time. All right, so I'm a proud alumni of IGIT. And so after IGIT, I graduated in 2011. After that, I went to IIT Kharagpur. And this is one of the photo with all my batchmates and the professors who used to teach there at the time. And after IIT Kharagpur, I worked in India for a couple of years. Then I decided to do PhD, a brave decision, I suppose. For anyone who is doing PhD, you do understand. So I moved to Melbourne. I did my PhD at Swinburne University. This is during my graduation, wearing a nice sari. And then I joined CSIRO after my PhD. So, and I'm working here since past 5 years now, or more than 5 years, almost 6 actually. So what is CSIRO and what we do here? So CSIRO is basically Australia's national science agency. So, and we are one of the largest multidisciplinary research organization. We have about 53 sites across Australia, and also we got a few in abroad. Somehow my slide sharing is off. Sharing is not turned on. Can you still see my screen or?
No, sharing is off.
You can share again.
Okay, all right. Can you see it?
Yes, it's not. Okay.
Okay. So we do a lot of state-of-the-art research. and we have the infrastructure for that. And also we have over 4,000 research partners, and we also work with a lot of industries. Next slide. Okay, some of the key inventions, the Wi-Fi, without which our life would be, I think, a lot more difficult nowadays. So that was invented at CSIRO. Our Australia's banknotes, which is a polymer note, that was also invented by CSIRO. There are a couple of other things in the slide. I'm not going to go through those. You can, of course, find them online. So CSIRO, like I said, works in variety of research areas. I specifically work in the mineral resources. So that's the business unit I work in. In the research unit, we have several groups, and I work in the green metals group. And like I said, we work in collaboration with many different organizations. I have just listed a few here, which I think might be relevant to the audience of this talk. The key one is the India-Australia partnership. So it's a 3.5-year program that's going on between CSIRO and many Indian organizations. The key ones are, I think, ISC Bangalore, where we are doing some biomass work, in IIT Kharagpur. Then I think there are a couple more, also IMMT. So there's a lot of projects going on in this area. We have about 10 projects in total in the green steel area, and also critical minerals research as well. There are also other initiatives like Hill CRC, ARENA, which are basically Australian, like primarily for Australian industries and partners. And I think if there are any students watching this, just have a look into this area, because we also have a lot of PhD postdoc positions that we advertise very frequently in several projects across this area. So now let's get back to the topic. So the topic is basically decarbonization in steel industry, right? So let me give you a brief idea about the iron and steel industry, just the scale of it, how big we are, right? So on your left-hand side, what you see is sort of like a big block. And what it shows is that about 2.6 billion tons of iron ores were mined in the year 2022. If you compare that to the right-hand side, then you can see that how bigger we are compared to aluminum and other industries. So this slide, what you see on the left is basically which are the major iron ore producers of the world. And as you can see, Australia is the biggest, right? It's almost 900 million tons of iron ores Australia mined, and that's followed by Brazil, China, and India. But Australia is not the major producer of steel. So the biggest producer is China. So what's going on here? So what Australia basically does is it just has the dig and ship model. So it just digs the iron ore and then ship it to China, most of it to China, and then China makes the steel. So, and India, as you know, we are the second largest producer of steel now. But if you just look at the scale of it, China is just producing more than 50% of the world's steel right now, right? So now this is quite relevant when I move to the next few slides. I think in the middle of my talk, you will see the relevance of this. So now why are we talking about the decarbonization? It's because steel is one of the majority, like you can find it everywhere, right? It's the most used metal on the earth right now. And if you look into the total global emission, the carbon dioxide emission or the greenhouse gas emission, then the steel industry actually contributes to the 7% of the global emission. And why is that? It's because like for every ton of steel we make, we produce twice the amount of carbon dioxide. So it's basically buy one, get two for free, right? And this is not like a shopping center where we should be happy, but this is like we are destroying our planet. So this is too bad for us. Now, again, I'll just ask the same question. Why is it relevant though? Like we know that CO2 is not good for our planet, right? But where are we at that scale? Why we need to be bothered right now? Like, you know, what is the necessity of it for this moment? So if you go back to the Paris Agreement, where the target was to lower the global warming by 1.5 degrees centigrade, the temperature, rising temperature, then the prediction right now suggests that by 2050, we need to lower the current CO2 emission from 2800, about that, to about 400 to 600 million tons. And at the same time, if you look at the steel sector, in 2015, we produced about 1600 million tons. Currently, it's about 1900 million tons. And the demand of the steel is going to rise, especially in the country like India, where we are just, we are developing, there'll be a lot of infrastructure going on. So the steel demand is expected to rise to about 2500 million tons by 2050. And that also means if you multiply that by 2, buy one, get 2, then we are also going to emit about, 5,000 million tons of CO2. And our planets cannot afford that. And according to meet the Paris Agreement goal, we need to lower that emission from current more or less like 1.8 or 2 ton of CO2 per ton of steel to about 0.2, which is about 90% reduction in the current emission that we need to achieve by 2050 in order to achieve the Paris Agreement CO2 reduction goal. So how do we do that, right? So how do we lower the emission from the steel industry? So in order to do that, you need to understand what is the how the iron and steel is made. So this is a very simplistic slide that I've prepared. So how is steel made? Or in fact, how is any metal made, right? So except for the noble metals like the gold and silver and all that, most of the metals, they occur in the nature as iron ores, right? They're not occurring as free metal. So they are often combined with oxygen. So they are in the oxide forms. So in the iron oxide, in the iron ore, so iron combines with oxygen and they are chemically bonded. So when you want to remove the oxygen from that ore, you can't just separate them out. They love each other so much, right? So you need to add something else which loves oxygen more than iron so that you can do their breakup. So, and what do we use? Is carbon or any source of reductant like hydrogen or maybe CO, right? So when you use these elements like C, CO, or hydrogen, then they love oxygen. So then they take out the combined oxygen and release just CO2. And in return, we get that metallic ion, right? And then metallic ion, of course, like this is a very simplistic way. In the actual practice, the process is not that simple. We have lots of these impurities like silica, alumina, which we call them as gangue, right? So the process is actually way too complex. But if you just look at the core of it, it's just that you are using a source of reductant or also the heat source, because these reactions usually happen at really high temperature. So you need to heat them up to really high temperature as well. So this is where the CO2 emission is coming from. So then how can we lower or completely eliminate the CO2 emission? Instead of carbon, you just use hydrogen, right? So that's the simplistic way to look at it. Now, let's look into the different way currently we make iron. So I have so this figure, as you can see, there is a lot of information. I was doing a lot of literature review during my PhD. So this is one of the diagram from there. So here I have classified the current iron making processes into two categories. One which uses coke and the other ones which does not use coke. So those are like coke-free iron making. So in the coke-based process, we have the blast furnace, which is currently the majority of the world's iron is made using that. And then there are coke-free iron making processes. And again, why coke-free? Why we have developed all of these coke making processes? And as you can see in this chart, there are literally like everything is coke-free except for the blast furnace, right? So what was the need for that? Well, coke itself is a carbon-intensive process, and it is expensive, right? So that was the necessity for inventing all these coke-free iron making processes. And in this category, we have basically two types. One is gas-based, like natural gas-based, and other is the coal-based processes. So now we won't go into the details of all of those, but just one more thing to highlight is that the Midrex, HYL, all of these shaft-based processes, they encounter for about 7-8% of the rest of the iron which is made. So it's basically blast furnace and then few shaft furnace sort of processes, which are currently used for making iron. Now, this is another way of dividing all of these iron and steel making processes. And this is a really good paper by Zulan. And what this one is doing is this is dividing all these iron and steel making processes based on its scale. or you can say based on the process itself. So the first is the blast furnace. So what blast furnace does, it makes iron in the liquid state, right? The process is very complex, but the basic thing is it operates at really high temperature and gives you liquid iron. Then there are smelting reduction processes. The scale of it is very small, like less than 0.5%, if I have to say. And they first make the solid iron, which goes to a melting unit, and it produces the liquid iron, similar to blast furnace, but it has sort of like two states, smelting and reduction. So that's why it's called the smelting reduction processes. Then there are DRI processes, which only make solid iron, and that goes to an electric melting unit or the electric arc furnace for the steel making. And then there are the scrap melting, which does not do any reduction. Basically, you take you have to recycle the existing steel scrap, and then you just make the steel out of it, right? Different grade of steel. So currently, in the current global scenario, if you look at it, about 70% of the total steel making is done through blast furnace BOF route, BF-BOF route, and rest 30% is done in electric arc furnace route, which feed direct reduced iron, which is the solid state iron, or the scrap. Now let's look into the emission. So unless we look into the emission, we can't do anything about lowering the emission, right? So we need to know how much of all of these processes actually emit. So as you can see in the graph, this is very self-explanatory. You can see the biggest one is the BF-BOF route, the blast furnace route. And if you do a little bit of a changes to the blast furnace, like adding the natural gas, or if you add DRI, then the emission is slightly lower. And then comes the DRI, which is the basically the natural gas-based processes, which comes the next. But if we want to really decrease the CO2 emission, we have to either go for the scrap EAF, so that is just recycling, or we have to go to the other end, the right-hand side, which is the hybrid process, which is basically the hydrogen-based process. I'll discuss about that later on. So what this slide is basically showing you is that for that 90% reduction, the first few slides that I explained, we need to achieve 90% reduction by 2050, right? So if we need to actually achieve 90% reduction, we can't just do some minor changes to the existing processes. We have to come up with something really unique, which can significantly lower the emission, like either the scrap EAF or the hybrid, right? So let's look into the scrap-based steel making. So if you want to do scrap-based EAF, what do you need? Scrap, right? If you don't have scrap, you can't make steel. So there should be enough supply of scrap for you to make the steel. Now, if you remember that number, the demand of the steel, or in fact, the last year, how much we produced, about 1900 million tons of steel. If you want to produce that, you need to have that much of scrap available. But if you look into the data, the prediction says that we will only have about 900 million tons of scrap available. So there is clearly a gap in the demand and supply of scrap. There are also other issues like scrap sorting, for example. So you can't just add anything, like any kind of scrap to the EAF. You need to have high-grade scrap. Otherwise, you will create a whole lot of problem, like you can increase the energy demand and all of that. So there are some other technical challenges associated with scrap other than the supply of it. So now let's come back to that figure again. So of course, we need to add scrap into our future steelmaking processes, but what are the other options? So then we can do sort of like changes to basically all three of those. And what are the changes that we can do? So let's first look into the blast furnace, the first bit, this one, right? So what can we do in the blast furnace? Well, before going into the changes, let's first understand how the blast furnace actually work. So I don't want to make it too complicated, but basically in the blast furnace, you charge different iron ore feedstocks from the top, and one of them is coke. And we need coke for basically three different reasons. First, it gives the reductant. So it takes out that combined oxygen out of the iron oxide and it makes the metal. It also creates a lot of heat when it is combust. And so you get the required heat for the melting of iron. And blast furnace usually operates at about more than 1600 degrees in the bottom part. So you need that heat. And the third and most important thing that coke does, it gives the strength to the burden. So if it doesn't give the strength, all of the top burden is just going to collapse, right? And we don't want that. We want that coke to stay solid until the top part reaches to the bottom. So that is one of the most important bit, which I don't think anything else that is available right now, which can be a substitute for coke. And if we find a substitute for the coke, we can still use the blast furnace for the net zero scenarios, right? Till now, we haven't found anything. So if we have to continue with the blast furnace, we have to use coke. So that is the most important bit that you have to remember. Unless some of you will come up with some exciting idea to replace coke, that's another thing. Okay, so now why is coke, what is the direct CO2 emission from coke making? So if you just look at the table that I have put here, it's about 0.8 ton of CO2 you emit per ton of steel, and that is quite a lot, right? So if you need to lower the emission, either you can lower the quantity of the coke, or you can have another fuel source to compensate for the coke. So like I said, coke serves two purposes, right? First as reductant and then the heat source. So reductant part, you sort of like, you have to have that coke in the top part of the blast furnace, but you still can have other source like hydrogen purged from the tuber region. And that's what some of the people are doing. So now this is the okay, so now this is the ULCOS project. I'm sure you have heard about it. This is a European initiative for lowering the carbon footprint from steelmaking industries. And this is one of the ideas where they are using the top gas, recycling it, removing the CO2, and whatever is the CO content of the off gas, then they recycle it from the to the tuber region. And this is one approach. And I think the latest trial where they use the recycled off gas in the tuber region and slightly above the tuber region, and they were successful in achieving 24% less carbon dioxide emission from the blast furnace. They have also used pulverized coal in the bottom part, and therefore they were able to lower the quantity of the coke that is required. Right, so this is one of the significant advancement that has been happening. But again, like, is it enough, right? Is 24% less CO2 enough for net zero iron making? So that is the question that you need to keep asking. Now, there are obviously some other things going on, like the German giant ThyssenKrupp. They have tried hydrogen in their blast furnace, and that was successful, obviously. But there is also a limit to how much of hydrogen you can actually put into the blast furnace. So I'll just explain the reactions, which is here for a little bit. So when we go back to the blast furnace and using the coke, and if you look into the reaction, then most of the reactions, the reduction reaction is actually exothermic, right? So for example, the hematite to magnetite stage is highly exothermic. But when you use hydrogen, that's actually very less exothermic. So it, instead of like releasing too much of heat, it releases small amount of heat. Now, if you look into the actual Uustite reduction, which is actually the rate controlling step for the iron oxide reduction. So if you look at that, then the Uustite reduction is actually endothermic. What does that mean? So that means if you go back to this, so if you purge hydrogen in this area, then the reaction is endothermic. So it will sort of like lower the rough temperature, the raceway flame temperature. And that also means the top gas will also have, the heat balance will be totally disturbed when you use hydrogen. So some of the solution that people come up with is, what if you just preheat the hydrogen and then use it in the furnace, right? And that also can help. But like most of the recent study, if you look at it, so what this suggests is about 15 to 30 kilogram of hydrogen is the maximum that you can put into the blast furnace. And that leads to about 8 to 30% reduction in the carbon dioxide emission. So again, this is not enough, right? We need to do more. So now I have just listed a few more examples. So this one's from India, from Tata Steel Jamshedpur. So they have done, I think, 3-4 days trial run with the hydrogen in the blast furnace, one of the blast furnace, successfully. There is another one in Japan, which is called Course 50. Again, similar concept. You create a hydrogen using renewable energy. You put the hydrogen in the blast furnace, and you also recycle the carbon dioxide that comes from the blast furnace, and you make ethanol or some sort of other fuel that can be used, and also recycle the top gas after separating the CO2. And this slide is actually quite interesting. So if you look into the current net zero commitment from many industries, like China, for example, like I said, they are the biggest producer of steel, right? And they have the net zero commitment until 2060. And India, for example, is 2070. But what are they actually doing? So in terms of the blast furnace BOF development, so these are the commitments, right? So they have committed to 158,000 ton capacity blast furnace, and this is currently under development. And if you know, blast furnace usually has life of about 40 to 60 years. So if they're building it right now, what does that mean? That means it's gonna last for another 60 years, right? They're not gonna just abandon it. So even if they have the commitment to net zero, which means like zero emission from steel industry or overall, they're still building the blast furnace. And why is that? It's because blast furnace is so effective and efficient, right? So yeah, so it's because the blast furnace is very efficient technology. So it can produce like, in terms of the scale, it's about 100,000 ton per day, if I'm not wrong. So the scale is huge. So and that's why we have like over 90% of current iron is made using the blast furnace. Okay, so now let's look into an overall picture of what's going on in this space. So as you can see in the headlines, there are quite a lot of investment going on in the steel decarbonization sector. That means there is a lot of money for researchers like you and me, and this is a nice time to be here. That means we have a job. So all of this investment that you were seeing, this is not for the transitional state for the blast furnace, lowering the blast furnace emission. Those are for new technologies, or at least using the net zero technologies. And so let's have a look into those. So the smelting reduction and the direct reduction technologies. Hisarna. This is one of the process which is quite exciting, and also currently they're producing. Just give me 1 second. Yeah. Okay. So Hisarna. So how many of you know about the high smelt process? You must have studied it during your bachelor time if you have done metallurgy. So that is one of the process which was developed quite some time before. And that was actually sort of like a bottom half of this process. And so the whole concept of high smelt was to use fines. Instead of agglomerating or making pellets and sinters, the idea was to just use fines in a bath smelting reactor. So you purge the gases from the top, and then you put the iron ore fines from the bottom, and then you make the liquid iron. Now, Hisarna is sort of the advanced version of the high smelt process, and this was invented as a part of the ULCOS as well, which is the TGR blast furnace that I discussed earlier. And the top bit is a cyclone, and that was patented from Tata Steel. And the bottom part, the high smelt process, is actually patented technology from Rio Tinto. So they came together, and then they decided to merge the technologies and come up with this Hisarna solution. So what does this thing do? So firstly, the top part, the cyclone, this is where the reduction happens, and a little bit of melting also happens. And then the melted iron, or the reduced iron, you can say, that drops to the bottom part, and then you make liquid iron. Now, this one, obviously the production is lower compared to the blast furnace, like 10,000 tons per day, the blast furnace. And this is, as you can see, it's very low. although it's a commercial plant, right? So the scale is very low, but the good thing is, instead of coal, you can use biomass, right? Or you can use alternate source of fuel. So this technology can certainly be made to net zero. Now let's go to the next one, the hybrid. This one is actually quite popular technology, and this has actually good potential, if I have to say, because the hybrid basically is a sort of like a replica of the current Midrex process, the shaft furnace process, where we make solid state iron. So on the left hand side, there is the blast furnace. On the right hand side, we have the hybrid process. So in the hybrid, in all stages, we are using renewable energy. So whatever the steel that comes out of it, it is going to be net zero. So let's look from the top. So once you have the iron ore fines or concentrate, you make pellets, and pelletizing needs some heat. So you use non-fossil fuels, probably some sort of bio oils or even hydrogen. And then the pellets go to a shaft furnace, which is again heated with hydrogen, and hopefully the green hydrogen, which comes from renewable sources. And then you make sponge iron or DRI. And then that goes to a electric arc furnace, which is again heated with the green electricity. So therefore you make green steel instead of the fossil steel. And this process is actually a Swedish company, and they came up with this. And they are planning to cut Sweden's and Finland's CO2 emission by 10% and 7%. So again, this is not huge, but still, at least there is a net zero product that you are getting without emission, right? Now, this is a technology called Calyx, so zero emission steel technology. This is actually an Australian technology, and this is about 2 hours drive from here. So the technology is very simple. It's like a falling particle reactor. So these are sort of like tubes, right? So each tube is basically electrically heated from outside. So if you look at the left side schematic, what you see is that dark blue is basically the electrically heated tube, and from inside you just drop the iron ore. It stays in the reactor for a few seconds, like a very low residence time. However, during the time, it gets reduced using the hydrogen, which is supplied from the bottom part of the reactor. So there is a counter current flow happening. And within that short span of the contact that's going on between the iron ore and the gas, it gets reduced. And you get that solid product, solid DRI, which can then again, you can either briquette it, ship it somewhere to make steel, or you can have a electric arc furnace right next to it and you can make the steel there. Now, this technology, they just received, I think this year's COP28, they received the award for the best technology. So just watch this space. This is a very, well, I mean, if I have to say, this process is actually not dedicated for steelmaking. So initially when they started, they developed it for, the magnesite and calcite decomposition. So the process, the concept itself can be applied to various sectors. But Jesty, as it is the Melbourne-based company, they are only focused on the steel. Okay, the circular process. Now, this one is very interesting because this is the world's first commercial hydrogen steel producer. So they have already made steel using hydrogen back in 2004. Now, you must have heard about the process as well, or even read about it, because this is quite an old process, right? So this is a fluid bed process. So it does not need to agglomerate the fines. It can work with just the fines, right? It doesn't need any sinter or pellet. So I'll just simplify what it is. So basically you have your fines, you preheat it at about 900 degrees centigrade. Then that preheated ore goes to a 2-stage fluid bed reactor. The top part is called circulating fluid bed, and that is heated to about 700 degrees. And this is where the main, the initial stage of reduction happens. You get about, I think, 80% metallization. Then that product goes to the second stage of fluidized bed, which is called bubbling fluidized bed. And this is where the final stage of reduction happens to about 95%. So the product that you get is about 95% metallized. And obviously there is a bit of a gangue as well. So this process actually, like I said, has been tested with full hydrogen, 100% hydrogen in the plant in Trinidad, USA. And they have tested it at 65 ton per hour production capacity. And over a span of few months, they produced 300,000 tons of zero carbon DRI using hydrogen. So what does this mean? This means that we can make steel using hydrogen, right? So technically, it is possible to make steel using hydrogen. But what can be the challenges though? So far what we have been seeing is there are all these companies which have promised to use hydrogen. Some of the companies already started using hydrogen. But what is the problem? Is it like that simple to make zero carbon steel? Because if you know, by definition, steel is an alloy of iron and carbon, right? So without carbon, can it be called a steel? Okay, so now let's look into some of the problems that I think is very critical. So if you understand a little bit about the steel making, you know that carbon is actually a crucial element in steel making because it does quite a lot of things. So like we discussed in the blast furnace, the role of coke, which is quite crucial. In the similar way, in the electric arc furnace steel making, the role of carbon is again very crucial. So what carbon does is when in the steel making, as you know, it's an oxidizing state, right? Because you need to oxidize all of those minor impurities like silicon, manganese, whatever, to its oxide form so that it can be taken out as slag. In that process, you also oxidize some of the iron and it makes oosteite, FeO or Fe2O3. Now, if you don't use carbon, all of that oxidized FeO or Fe2O3, that will just go in the slag, right? So you will have metallic loss. So in order to convert that oosteite back to iron, you need to have some form of reductant in the system, in the electric arc furnace. And that's where the role of carbon comes in. And so firstly, it reduces the FeO, which otherwise would go to slag. It also helps in creating bubbles, the CO bubbles, which keeps the bath steered. So there is uniform mixing inside the bath. So the role of carbon is actually quite significant. So we need to have some alternative to this to find a solution, like what will happen if we just skip carbon from electric arc furnace, right? Or we can use some sort of biocoke or biomass based carbon to continue doing this, right? There is also another thing that you need to know. So if you remember the iron carbon phase diagram, what does it say? So when you increase the quantity of carbon, the melting point of iron goes down, right? If you're not adding any carbon, then the melting point of iron is actually higher. So now all these hydrogen-based steel-making processes then again have to operate at slightly higher temperature, or the heat demand basically in short term, that's gonna go up, right? All right, enough about the problem. Let's go back to some of other news. So this is BHP, Australia's one of the largest iron miners. They have partnered with POSCO, which is a South Korean company, to advance the hydrogen iron making pathway. And their process is called HYREX. Now, HYREX again is a advanced or hydrogen version of the FINEX. FINEX, again, you must have read about it in your alternative iron making textbooks. So if you look into the blast furnace and FINEX, you can clearly see there is a lot of differences. FINEX, like the name suggests, it works with the fines. The blast furnace works with the agglomerates like sinters or the direct shipping ore. Now, so in the FINEX, there are multiple or multi-stage fluidized bed reactor, which is reduced using the off gas of the bottom part, which is called the smelter gasifier. And so the DRI, which comes from the fluid bed, DRI fines basically, that is melted in another vessel to make liquid iron. Now the hydrogen version of it, which is called HYREX, looks like this. So you have again the fluidized bed, multi-stage fluidized bed, which will be reduced. Instead of using the top gas from the next stage, it uses green hydrogen to reduce the DRI. And then that DRI goes to an electric smelting unit, which is basically electrically heated. And you melt the DRI and you then convert it to steel, right? So this is another version of IREX, another version of the hydrogen steel making. Now there is another process. Again, it's a fluidized bed. This is a collaboration between Prime Metals and Rio Tinto. And the process looks like this. So you will have again a fluidized bed, and that will go to the steel making stage. Now here I want to highlight one more thing, which is the DRI melter. So, okay, so I think I can easily explain in this one. Okay, so in this process, we are not even bothered about the quality of the ore so far, right? So what happens if your ore has higher amount of gangue, higher amount of these, the unwanted substances? So in that case, if you directly make the DRI with higher gangue, then that needs to be taken out during the steel making stage, right? So what people are actually suggesting is to have a melter stage in between. So instead of taking the DRI directly to the electric arc furnace, you then melt it out in an intermediate stage. And that is the electrical smelting stage. So this, watch out for this area as well. There is a lot of research going on in that space. Now I think I'm just running very, very slow, so I'll just fast forward. So this is another technology called hydrogen plasma. So there is quite a bit of research going on around the world. In IMIT Bhubaneswar, they are also looking into hydrogen plasma. This is a really good paper, one of the first paper actually on hydrogen plasma. And as you can see in the Ellingham diagram, hydrogen itself can reduce a lot of oxides, right? But hydrogen plasma, if you look at it, this is just massive. So if you can use hydrogen plasma, you can basically reduce anything on the top of the Ellingham diagram. And that's what people are doing. So you create a hydrogen plasma using DC or AC arc, and then basically let that reduce your iron oxide. This is one of the examples. This is a Austrian company, Fosterpin and K1Met. K1Met is one of the research organization in Austria. And they have come up with this hydrogen plasma design. So basically you feed the iron ore from the top, and then it will be reduced using the plasma. You can read more about it. I'll share the slides. Okay, so enough about the hydrogen use in the shaft. Now let's look into something different, which is electrolysis. So what if we remove the carbon entirely from the equation, right? So if there is no carbon, then it will obviously be there will be no CO2 emission. So you don't have to use actually hydrogen, right? If you are using something else, which is the electricity. So the concept behind electrolysis is, instead of using electricity to make hydrogen, what if you use electricity directly and remove the carbon from the equation? And that's what actually people are doing as well, some of the people. And I think Ulcos has quite a lot of electrolysis work going on as well. So this is one of the video that you can see what's going on in here. So you drop the iron ore in the electrolysis cell, and then, so this is the technology for Boston Metal, and they have actually not shared what the electrolyte is, so it's their patented technology. So when you put the iron oxide into the cell, it dissolves with the electrolyte, and then you have an anode and a cathode, and during the electrolysis, your iron oxide is actually reduced to metallic ion. And then you tap it from the furnace, or from the electrolytic cell. Now, instead of a schematic view, just have a look at this video. Okay, so the reason I included the Boston Metals electrolysis technology is because they recently won the Times Magazine Best Decarbonization Technology Award. And that is quite interesting because we have been using electrolysis for aluminum industry, right, for quite a long time. So can you imagine using the electrolysis for this massive scale of for iron ores? Can you imagine that? And also, you also need to consider that it's not just one cell. You have to, for the scale of our 2000 million ton or 1 billion or 2 billion tons of steel production, how many of these electrolysis cell you need to have to meet the demand? There is also certain things which are not very clear, like the lifespan of the electrodes, the anodes they're using, and it's just very difficult to imagine the scale of it as well. But of course, this is possible, and this is a unique way to look at it. And Boston Metals process is actually a high temperature electrolysis, but there are also several lower temperature electrolysis processes as well. Now, this is another slide which is showing the technology readiness of different processes that I just discussed, like the hydrogen-based shaft furnace processes, hydrogen-based fluidized bed processes like the Hyrex, the POSCO's one, all that, and also the plasma and electrolysis. So the most feasible option that you can see from here is basically the hydrogen-based shaft furnace category, which is basically the hybrid type of process, or the HYL's energy ion kind of process, which is shaft furnace using hydrogen to make green steel. So their technology readiness is very high, and their development cost is very low, and this looks quite feasible actually. So what does this mean? Is the hydrogen the total solver of all of our emissions from steel industry? Let's look into it. So hydrogen, when somebody says hydrogen, it can be from any source. So currently, if you look into the right-hand side figure, only 3% of the percentage of the current hydrogen produced is actually green hydrogen, which is carbon neutral. The rest of it is either sourced from methane or from coal. So as you can see, there are different colors: blue, gray, purple, pink, whatever. And the green one is actually the hydrogen produced from the electrolysis process with renewable energy. There are different types of processes, electrolysis processes: alkaline, proton exchange, and solid oxide. The alkaline one is the most mature technologies that is currently being used. Then there is the proton exchange membrane, which is highly efficient, if I have to say. Solid oxide is still under the demonstration stage. Now, in the context of the steel making, so the ThyssenKrupp, which is the German steel makers, they're working with to make a 300 megawatt electrolyzer for green hydrogen plant. Again, there's another in 2021, Air Liquide had an electrolyzer of 20 megawatt capacity. Now the new one that is coming up is from BASF, which has just commissioned 54 megawatt water electrolyzer. What does this mean? What is this capacity in terms of the scale of the steel making? So the International Energy Agency, they estimate that we would have about 411 million tons of DRI per year during the net zero scenario, right? And in order to achieve that, we would need about 11.5 million ton of green hydrogen. That is quite a lot. So if you just read the bottom line, you would see how big of a difference in the current hydrogen production scale compared to the actual green steel demand, right? So we need to do quite a bit of research in the hydrogen production category so that the cost can be lowered, and also the whole hydrogen production thing can be integrated into the current steel making pathways. Now, in terms of the cost, currently, obviously, the cost of hydrogen will be different for different countries, because in some countries, the renewable energy is very cheaper compared to countries like us, in India, for example. So if you look at the cost, in some countries, it's about $12 per kilogram. This is US dollar, and that is quite a lot. And in Sweden, for example, where they are using hybrid process, using hydrogen, they have about $4, so which is still better compared to $12. So these countries can certainly focus on using hydrogen for making steel, right? If they have to. So there is a bit of a balance that needs to be made. So not every country actually can afford to use hydrogen for steel plant. Now there is a lot of investment going on as well. So that's this is sort of my summary slide for the hydrogen. So is it a hero or a hype? So there are a few things that you need to know, that hydrogen firstly can make our industry net zero, but it is highly expensive. It has the technologies of hydrogen production. Some of them have low TRL, like the PEM technology, proton exchange membrane. And how do you integrate the hydrogen supply to the steel making plant? Like, do you have a pipeline, or do you generate hydrogen right across the steel making unit? So that is one of the questions. Now, I think I've been speaking a lot so far. Do anyone of you have a question, or I shall just move to the next stage?
We can take up questions at the end, okay?
At the last? Okay,
Nice.
then all right. So let me go back. Oh. Okay, so now other than hydrogen, what else can we use to lower the emission? Biomass, right? We have been using biomass since a long time. Like when the iron making was started, they were using charcoal, right, to make iron. So are we going back to that historic age of using charcoal? Well, at least the research says we probably are. So this is a really nice summary of where we can use biomass for a net zero iron and steel making scenarios. So in the blast furnace, the first column, you can see that we can either use it in the pellet or sinter making stage. We can use it, you can make biocoke as sort of like a replacement or partial replacement of the coke in the blast furnace. In the shaft furnace processes or the DRI based processes, we can use biomass in the for example, in the melter gasifier, in the Corex kind of processes, or even in the electric arc furnace, you can use biocoke as a source of carbon, right? Similarly for the EAF as well. So there are multiple options where the biocoke can be a good fit, and it can lower the emission to various amounts based on how much you can use. Now, in this context, other than the blast furnace, we also have a lot of rotary kilns, which are coal-based processes, right? So in those processes, you can certainly use replace the coal from using biomass. Now, this is another process called ITMK3. So back those days when it was invented, they used to call it third generation iron making process because of its lower emission from the blast furnace. Now, the process itself, it works with the composite pellet. So you mix the iron ore with coal, you make the pellets, then charge it to this rotating hearth kind of reactor. And because of the close contact between the iron ore and the coal, the iron ore gets reduced very quickly, like in 10-12 minutes, I think, and then you get these iron nuggets. Now, this is one example, like a really good example, where you can substitute the coal with the biomass. Now, is it then the solution? Can we then just use biomass instead of this expensive hydrogen? There are a lot of questions around it. Like, firstly, I would say the supply side of it. Can there be enough biomass? Can we have that enough supply to make the 2 billion ton of steel that we need right now? The second question is the social acceptability, because just try explaining that to these teenagers, or the future, the people who are going to lead our future, that we have to plant trees and then we cut it down, then we use it for our furnaces. So it's a very hard thing to accept mentally. And how are you going to make sure that you are planting the same amount of tree that you are chopping it off, right? So there is a sort of a balance. So it's like that carbon capture acceptability. The social acceptability is quite the key in case of biomass. In some places, like in Brazil, for example, you can probably think of using biomass as a solution. There is a currently project going on between CSIRO and IISc Bangalore as a part of the India-Australia initiative, where we are looking into use of biomass, like the agricultural waste for making biochar, and then you can use that for making iron. All right, so just to conclude this bit of the talk, there are a lot of things that's going on in this space. There are a lot of ideas, a lot of solutions people are thinking. And this sort of like the summary is from the International Renewable Energy Agency. And as you can see, there is a lot of things going on. So I don't think it's going to be a very straightforward, simple one solution for decarbonizing. I think there will be multiple solutions, each dedicated to for each country or for each kind of process. So it's going to be a very complex area, but the good thing is there is a lot of interest seen from the government and also a lot of funding coming from the industry. So it's a good time to be a researcher in this field. So now let's look into the second aspect. I think I still got a lot of time. So this aspect is basically looking into the mining side of the things, and how can we process, or how can we sort of like improve the quality of the ore so that we don't have to take them out during the heating stage. So what is going on with the iron ore quality? So if you look into the current data, currently we have only 3% of the global iron ore which are suitable for this direct reduction, which is basically you can say suitable for the future net zero steel making. So, and 3% is not a lot, right? And what does that mean? So that means that currently, if you look into those iron oxide grades or the iron ore grades, that means we are getting higher amount of this gangue like silica and alumina. And if you look into this slide, it shows that over the past few decades, you can see that the percentage Fe, the fixed amount of iron that is in the iron ore, is actually declining. And as of 2021, we have about 8% of the gangue in most of the sinter feed. Now, this data that I've generated is actually using 130 different iron ore feedstocks. And as you can see, these are the different types of feedstock that goes to the current iron making processes like sinter fines, magnetite concentrate, pellet feed, and also lumps. And you can see the gangues in each of them, like how they are sort of like really high. So what happens when you have this higher amount of gangue in your iron ore, and then you process those high gangue containing iron ore to the iron making? So when you melt them or when you make steel out of them. So this is a really nice study. This is from the Mineral Council of Australia. And what it shows here is that if you have silica in your feed, and if the silica amount is just two times higher, then you need to obviously add slightly higher amount of lime, right? You need to maintain that basicity of the slag. And that actually increases the slag quantity, not very much. But if you compare that with alumina, just a small amount of alumina can increase the slag quantity by 6 times, because alumina actually makes the slag very viscous, and that is not good. You need to add more lime. That means you are creating more slag. And then what do you do with those slag, right? Because the composition is now changed as well. Will that be acceptable for the cement industry? Or, so how are you going to then make sure that the slag quantity or slag composition is acceptable for the cement industry? How are you going to make sure that the slag quantity is less? So there's another problem with the phosphorus. So the people who are working in the steel quality or the new steel development, you must know that phosphorus is actually very detrimental to the quality of the steel, creating just a nuisance. So this is a really interesting work that one of my colleagues has done, looking into where the phosphorus actually is located in the iron ore. So what their conclusion was that phosphorus is mainly located in the goethite or actually mainly in the goethite, the earthy goethite or the vitreous goethite. So somehow, if you can separate that goethite in the early beneficiation stage, then we can get rid of a lot of phosphorus. And there has been a lot of processes going on, like magnetite roasting. So what if you just roast all of these iron ores, convert the hematite goethite into magnetite, then do magnetic separation and remove all the gangue, right? Then you get really high grade ore. So you don't have to heat the gangue up later in the iron making stage. There is also leaching, a lot of research going on in leaching. Can you leach the gangue out of the iron ore? And can you improve the beneficiation technique, the current beneficiation techniques like, the flotation or gravity separation? Can you come up with something new which can actually remove all those dirty stuff very efficiently without losing much of your actual iron oxide? This is another slide. This is sort of a summary of different iron oxide deposits. We won't look into the geography, but what's more important is the bottom bit that I have highlighted. So it's not just the quantity of the gangue that is changing. So it's not just the quality degrading, right? It's also the amount of the lump. So now if you see, there are a lot more fines that are being produced when you are mining all of the iron ores, because so far we have been using a lot of these high grade direct shipping ore. Now we are mostly left with the fines. So what do we do with the fines? Can you put in the blast furnace or the shaft furnace? No, right? Because they'll just choke the furnace. So currently, about 99% of the iron are produced using these shaft furnace processes like blast furnace, midrex, HYR, and all that. And rest 1% actually uses fines. So what do we do then? So let's look again into all of these iron making pathways in terms of, or in the eyes of the iron ore. So if you look into the iron ore, then the lump ore goes to the blast furnace. The fines then has to be either agglomerated like sintered or pelletized, and then they either go to the blast furnace or the other shaft furnace processes, or you can straight away use the fines in the fluidized bed kind of reactor like the Phoenix or the the HYFOR, Hyrex, or even the Calyx kind of processes. So now you have this intermediate agglomeration stage, which is again a high temperature stage. So if it is high temperature, if you're heating it with some sort of like fuel, that means again you are increasing the emission, right? So let's look into what are the current processes which are being used. So far we have only looked into the iron making, a bit of steel making, and also a little bit of initial, the not so much about beneficiation, but about the quality. But we have not discussed about agglomeration yet. So what's new that's going on in the agglomeration space? So currently we have either sinter or pellets. So in the sintering side, there is a bit of research on using hydrogen in sintering and also using like biomass based fuel. And in the pelletizing, there is of course research on bio oil. Can you use bio oil or even hydrogen? There is a lot of research on that area. So there is one process that I am currently working on, which is the LMP process, which I'll just explain a little bit. So in the conventional pellet process, so what we do is when we start with magnetite, it goes through a two-stage oxidation process. So the pelletizing is basically happens in oxidizing condition. So you have magnetite, you oxidize it to hematite, and then later when you charge your pellets to the iron making stage, you take out that added oxygen. So it's foolish, right? You are adding oxygen to the magnetite just to take out that added oxygen later on. That means, you're not doing good work. So the process that we have developed, it's called LMP process, where we maintain mildly reducing condition during the pelletizing, and we retain that oxidation state of magnetite, and then we make lime magnetite pellet. Now, what is lime doing here? So if you look into the magnetite, it's actually very dense. It's very difficult to reduce it to iron. So instead of just adding magnetite, we add a bit of a lime to make a sort of like a more reducible phase, which is this CaFe3O5 phase, the oxide phase of lime and magnetite. And as you can see, they have this platelet sort of shape, which are interconnected to each other, that gives the required strength as well as the reducibility. So we have tested these LMPs for their metallurgical properties, how they behave, how they compare with the commercial pellets and sinters. And so far we have seen quite good reducibility in all of them. And in some of them, the strength are very comparable to the industrial grade pellets and sinters. So, so we have mostly done the laboratory test, and now we are synthesizing them in the pilot scale. And most recently, I have secured about $2.6 million funding from the Australian Renewable Energy Agency. And I also have received the support of many industry partners. So the total project cost is about 5.3 million. And the main thing that we are looking at currently is to test this process for hydrogen. Can we make these LMPs using hydrogen? Can we make this using low-grade iron ores, like higher gangue containing iron ores? And can we improve the quality of that pellet? So that's mainly the process. And currently we are at TRL level of 4. We are obviously trying to improve the TRL and the commercial readiness. And of course, the process itself, because of the process, we have received many awards recently as well. This is one of the photos with the ministers. It's not very often you get to click a photo with the ministers, so I thought I'll just highlight that. And the award on the left side, this is again the Net Zero Emission Industry Award in COP28. They gave me the award for this, for developing this process. All right, so that's mainly the talk. I just want to highlight 2 more things, which is the dry slag granulation. This is one of the process that was invented at CSIRO. So the main idea is you recover the heat content of the slag, which comes out of the blast furnace at about 1500 degree. So this was, I think now it's being commercialized at a Chinese engineering company called MCCE. So they are doing a commercial scale plant very soon, I think. Then the high smelt process, it was, of course, the technology was invented at Rio Tinto, so the patent belongs to them. But most of the modeling work was actually done in one of our team. So one of our teammates, they did the work back in 2004 or 6, I think, when this was being developed. And now, as you know, the high smelt is being developed as Hisarna by the Ulcos using Tata Steel and Rio. The Cyrosmelt process, this is another reactor which is just next to my lab, and it was invented again at CSIRO. And currently the technology is being used by Isosmelt, which is from Glencore Industry, and also Osmelt from Autotech. So they're using it for mainly non-ferrous metallurgy, but you can also use it for ferrous. So that's mainly it. I hope I did not make it very boring for you guys, and I hope you learned at least something from the talk. You can find some of my papers and more about me by scanning the QR code. Just one more thing before I give you guys for questioning me. There is a symposium. This is the 7th AIST symposium. So the Association for Iron and Steel, they have a branch in Australia and New Zealand, and we are organizing a symposium again at CSIRO. It is online, you can join. For the student, it's actually very cheap registration. But if you're an AIST member, you can basically get it just in $50. So it's a 2-day talk, very interesting talks lined up from industry as well as from academia all over the world. So as a part of the committee, I think my job was to advertise it. So I hope I did that. Now it's open for question.
Thank you, Suniti. So if participants have any question, they can unmute themselves and ask.
I think I can read some comments from here in the chat. So as you are Indian, can you say how much technological advancement has India achieved in recent years, and to what extent has the country adopted and integrated advanced technologies across various sectors? That's a very nice question from somebody who I know dearly. Yeah, so I think the India's green net zero target is 2070. So I think the priority is not so much towards adopting, the green steel, but I think I gave an example about Tata Steel using hydrogen for one of their blast furnaces in Jamshedpur. So that is a really good start. But there is also, I think, some of the companies, they're working on hydrogen production as well, green hydrogen production. So this is again like my view. So what I feel is like India always let others do the work. And if it works, then India follows. So let's say if the Europeans are going ahead with green or net zero steelmaking processes. And if it works, then I think India will slowly start adapting to them. So, and in terms of like as a country, India is still growing, right? We have a lot of demand for steel right now. So we can't rely on this really expensive, like 3-4 times expensive steel based with hydrogen, and just abandon all our coal. We can't do that right now. We can't afford to do that. And again, like that's my personal view. I'm happy to be challenged on that. So what global standards and interoperability frameworks are needed for data exchange between steel producers, suppliers, and end users to create a transparent, verifiable green steel certification system? Yeah, that is I would say, difficult question. Yeah, so I think that is it's sort of like a probably somebody from the policies can probably better answer that question. And honestly, I haven't done much research on the classification or the certification system. But I would say, like, if a country like Europe is investing so much in the green steel research, and all of their, like, for example, I think in Europe, the government has asked all the steel makers to sort of like abandon all of their coal-based processes and shift to the green case, right? Because their net zero target is very near. Like some of them have like 2030 as the net zero emission target. So in that case, and the government is obviously giving subsidies to all these industries. So if you're investing so much, then why would you not have a green certification system, right? Because you need to create the demand for the green steel or whatever green thing, right? Because you are spending so much. So I think that is highly justifiable. And but I think that should be like, if you are coming up with that, then obviously you need to share the system, the certification system. Like no one can, like sort of like cheat in that process. All right. Let me go to the next one. What is the critical role of digital twin technology in the design, pilot testing, and operational ramp up of first of a kind low carbon hydrogen dairy facility, mitigate investment risk? Right, I'm not sure what is digital twin technology mean, actually. Nitish, so you probably have to look it up. But in terms of the investment risk, let me tell you one thing. I think in one of my slides, I had shown you that there are many steel makers right now which are abandoning the idea of green steel, like the hydrogen-based green steel. And some of them are even, like the conferences that I'm attending, some of them are even saying that the hydrogen steel is actually dead. Like, so they're not like very hopeful with the hydrogen DRI facilities. But it's not a time to get disheartened, I suppose, with, like ArcelorMittal, they're just, changing their plan to investment, all of that. So we shouldn't get disheartened. There is still a sort of like hope for hydrogen. And yeah, like I said, I don't understand the digital twin technology, what that means. How does process integration of hydrogen electrolysis unit with DRI plants affect the thermal management and overall plant exergy efficiency? Wow, I'm getting some tough questions. Integration of electrolysis units with DRI plant for the thermal management. Yeah, that's actually a very nice question. And I think there is a lot of research going on in that area as well. Like just the process integration itself is very tricky. Like you need to have that scale of hydrogen production plant right next to a steel plant. And like, firstly, that should meet the demand. And you are not even bothered about the land area, right? That is another thing that you need to consider. And hydrogen itself is not so safe, as you know. So there are a lot of challenges. So it's, yeah, like I said, it's like a very evolving research area. So you need to look out what is the latest sort of like innovation that has happened. And I'm not an expert in the hydrogen production side, so I'm afraid I can't answer that question as well. And that's, I think, all the comments. If anyone wants to ask anything, just still have a lot of time, about 10 minutes. It's good. There are, I think, 65 participants. Oh, wow, that's good.
Any other questions from the participants?
You can just unmute yourself and ask me.
Yes.
Mainly on iron and steel making area, maybe not mainly on hydrogen production side, because I'm not an expert in that area. So I think I'm not sure the category of audiences you have, but maybe I think I can give you some insight, because I think there's quite a bit of a time left. So some of the insights on like how do you actually do the research, right? Because this is a really evolving area, and I think this is a fantastic time to be a metallurgist in our field. And because this is a faculty development program, I think my sort of experience in the research might be helpful. Like how do you pick the research field, and how do you actually do the research? So I mean, everyone has their own way, but I think what I find most effective is finding the right topic is the key. So what is the hot topic that you need to do the research on? That is the key. The second stage is finding the collaboration. So for example, in IGIT, I'm sure like we have like a few labs with some of the furnaces, but still like, is there a better option for us to do the research? Like, can we just approach some IITs or CSIR, IMMT, some of the labs, or NML? Like, can there be somebody who can help in doing the work? I think that is another thing that we should start looking for at the beginning of the research. And the more collaboration we get, the better is the output, right? That is like the key. Because like here, at least like after working at CSIRO, I know that we have at least like 10, 20 partners that we are working at the moment. So it's the key. The collaboration is the key. The third stage, obviously, when you start doing the research, you have to, of course, like you can do it in a smaller group. But if you have a couple of students that you can sort of like, the master students or PhD students, which you can get the work done as a faculty, I think that's a good idea. Instead of you going to the lab and doing the work, just expand your group with, you can pay a little bit for PhD, maybe for bachelor projects, you don't even have to pay for them. So, you can start working on that area as well. And then the actual research comes. So when in the actual research, modeling is one of the key bit that can help you. And without modeling, I think it's like, for example, in our case, in the metallurgy case, you can do thermodynamic modeling using FACSAGE or HSC sort of software. If you don't have access, find a collaborator who has the access. So that makes your life a lot simpler. And then the actual research comes. So far, whatever I've seen in the research field, all of these works that's been going on in the fundamental study is basically done in a small, simple furnace. You just have to, if you have a furnace in your lab, basically you can do all sort of designs to that, make it a fancy equipment. But most of the PhD students that I have seen, or like at least during my PhD, we have developed our own sort of experimental rigs just using a simple furnace. And you can do it like anywhere. You can do it even in your backyard. If you have a furnace, you can make pig iron out of it, right? So that is the key. So it's not about the high-end research capacity that you need. It's just that you need to have that intention and the planning beforehand. You need to design the experiments accordingly. And of course, publishing is also the key, because without getting the exposure, there is no way you're gonna. I mean, so one of the things that we scientists or researchers, which we don't do that good, is promoting ourselves. Like, if you look into the Boston Metal, they're everywhere. So it's a really good idea to just promote yourself or what your research group is doing. So I think that is another key to just help getting the partnership and collaboration, and also the funding. There's no other question.
Thank you, Suniti, for a very nice talk. on sustainability of iron and steel making, mostly the decarbonization part. It's nice to know about your invention, that is the lime magnetite pellet, which looks very promising, this thing. So thank you very much.
So it's a pleasure,
Thank you.
to
Thank you, Suniti.
thank you. It's actually like really nice to meet all of you after so long. And obviously it's a pleasure to give a talk to at IGIT especially.
Thank you. Thank you.
Okay, then I think we should say goodbye to everyone. And it's almost night here. It's about 9 p.m. here, so I would better go something to eat and sleep.
Okay.
Okay, then bye-bye.
Bye-bye. Good
Bye.
night.
Bye, good night.
I think we'll wait for the next speaker to join. Good afternoon, everyone. So we have with us our next speaker, Professor Sibrat Singh. He's the professor and head Department of Metallurgical and Materials Engineering at Indian Institute of Technology, Kharagpur, and also is the chairman of the Steel Technology Center there. He has done his Bachelor's of Engineering from B College, Sipur, and then Master's Engineering from Indian Institute of Science,
Amulya?
Bangalore. Uh-huh.
Amulya.
Yes, yes.
Sir has not joined till now.
Sarah's joined, na? Sure. Yes, sir. Sarah's joined. You can make him co-host.
1 minute. No, sir has not joined. We can wait. Yes, sir has joined. We can start.
We have with us our next speaker, Professor Sibrat Singh. He's a professor and head Department of Metallurgical and Materials Engineering, Indian Institute of Technology, Kharagpur, and he's also the chairman of the Steel Technology Center there. So he has done his Bachelor's of Engineering from B College, Sipur, and then Masters from Indian Institute of Science, Bangalore, and PhD from University of Cambridge. He has briefly worked in R&D at Tata Steel and then joined IIT Kharagpur in 2000. And he has around 155 numbers of publications in peer-reviewed journals, several book chapters, and 11 granted patents. He's the elected fellow of INAE 2024, Endeavour Executive Award 2011 by the Australian government, DAD Fellowship in 2007, Young Metallurgist of the Year Award of Ministry of Steel, Government of India in 2003, Nehru Cambridge Scholarship 95-98, and then British Chevening Scholarship. His areas of interest is mostly on physical metallurgy of steels. On behalf of the entire team, I welcome Professor Sibrat Singh to this faculty development program. I think it's over to you, sir. You can start your presentation. Thank you, sir.
Sorry. Sir, you are in mute. On. Mute.
Can you hear me now? Can you hear me now?
Yes, sir. Yes, sir. We can hear you.
Okay. Okay, let me. I think there was some issue with Zoom.
Yes.
Okay, let me share. Can you see my slides?
Yes, sir.
You can see my slides, right?
Yes.
And I'm audible clearly.
Yes, sir.
Okay, so good afternoon, everyone. Sorry for that small glitch. So, this afternoon, I'm going to talk about some interesting aspects of Bainite transformations in steels. So to begin with, I will first highlight why is it important to study Bainite transformation. That is because it is an important component of microstructure in quite a few varieties of steel. To begin with, I will give you an example of trip-assisted steel and retained austenite. In this steel, retained austenite plays an important role, and and we obtain retained austenite because bainite is an important constituent of the microstructure. So, sorry, you can see this.
Yes, sir.
So, typical microstructure of transformation induced plasticity aided steel. It comprises of about 50% ferrite. So, the carbon content of this material may be about zero point 0.2 to zero point 0.4. So carbon content isn't too high. Therefore, transforming to bainite and retaining a significant amount of austenite is difficult unless austenite is enriched with carbon. So austenite enrichment of or carbon enrichment of austenite is carried out in two stages. First, transforming the material to ferrite by treating in the intercritical region, and once we have 50% ferrite, it is again subjected to an ostempering treatment or isothermal bainite treatment in bainite region to form about 20 to 30% of bainite, resulting in further enrichment of austenite. And when austenite is sufficiently enriched with carbon content, so that its MS temperature is below room temperature. Upon final quenching from the Austen-Pling temperature, a certain amount of austenite is left untransformed. So the microstructure is therefore 50% ferrite, 20% or 30% bainite, and the rest is retained austenite. This retained austenite is very important because it undergoes deformation-induced transformation to martensite during deformation, resulting in very exciting properties, which are listed here. One can see that for if you compare dual phase steel and trip-aided steel has higher YS and higher UTS, and yet it has higher elongation as well, and it has higher strain hardening coefficient because of the trip effect. And one can see not only is the total or average strain hardening exponent important, it is also important. What is also important is how N value changes with strain during deformation. For typical high strength low alloy steels or dual phase steels, after initial strain hardening, the strain N value decreases. Whereas in trip-aided steels, because of the transformation of austenite to martensite during deformation, it is able to maintain a steady N value during deformation, resulting in better elongation or ductility of the material. Now, normally there is a direct correlation between the product of UTS and total elongation with the volume fraction of retained austenite and carbon content of retained austenite. It is very obvious that the mechanical properties, we call the y-axis is the strength ductility balance, because we know as the strength increases, typically ductility decreases. As therefore, strength into ductility can be taken as a measure of strength ductility balance, and it scales directly with the amount of retained austenite and its carbon content. Why is carbon important? Because carbon content of retained austenite decides its stability against transformation to martensite. So the importance of retained austenite I did not overemphasize because it controls the mechanical properties, and we get austenite we get this return loss, right, because of the processing cycle that this material is subjected to. So there are two ways in which this material can be processed. One can one can after hot rolling is conducted, one can do cold rolling. One can do cold rolling, and after cold rolling, the material is subjected to an intercritical treatment between A3 and A1 temperature, where about 50% of ferrite forms. But the enrichment of austenite at this point is not sufficiently enough to enable it to be retained to room temperature. Therefore, further enrichment of austenite is carried out by doing an isothermal bainite treatment or austempering treatment in the bainite region of the TTT curve, where about to 30% bainite forms, resulting in sufficient enrichment of austenite with carbon, which is then retained in the room temperature microstructure because its MS temperature is very low. Even if it has slightly higher MS temperature, only a small amount of martensite will form, a majority or a substantial amount of retained austenite is retained. An equivalent microstructure can be obtained in directly hot rolled material itself by cooling it in such a way after hot rolling that during cooling through the ferrite region, it forms about 50% ferrite, and then cooling through the bainite region, a significant or 20-30% amount of bainite is formed, and then it is coiled, where martensite transformation does not take place because austenite is sufficiently enriched. So the microstructure at the end of processing is ferrite plus bainite plus retained austenite. So typically, if we need there, if we have to model this process, what we can do is we can calculate the phase diagram. That is what we have done, and calculate the temperature at which we can get 50% ferrite, and after that it is transferred for austempering or isothermal bainite treatment to a temperature in the bainite region, where as I will discuss, bainite transformation is limited by the T0 curve. T0 being the temperature at which austenite and ferrite have the same free energy. And once the T0 curve is calculated, we can calculate at any austempering or IBT temperature what will be the amount of bainite that would be formed. And it will also give us the carbon content of retained austenite so that we can predict its MS temperature and control the microstructure. So this is a simple calculation which has been done using this model, where what you see is how carbon content of retained austenite and phase fractions vary with the IBT temperature. X-axis is the IBT temperature decreasing from right side to left side or increasing from left side to right side. And using these calculations, one can see that there is a particular IBT temperature where the retained austenite amount is maximized so that we can exploit its benefit for transformation induced plasticity. So the bainite transformation is key to obtaining correct amount of retained austenite having correct stability so that it gives us benefit in terms of transformation induced plasticity effect. Okay. Obviously, if you have to calculate various phase fractions, then phase boundaries have to be correctly known. And as I will address that, how we can do that. My second example is in developing carbide-free benetic rail steels, where we once again our understanding of bainite transformation is used to design this material. So typically the rails on which railway trains run is made up of a perlitic steel, and a braided butter grade of perlitic steel is grade 880 material. This is typically a eutectoid material having 0.6 to 0.8% carbon and having a small amount of manganese, where it has a YES of 460 MPa, UTS is 880. That is why it is called grade 880. But its elongation is only 10% because the microstructure is based on perlite, which has significantly large amount of cementite. Therefore, it does not have very good ductility, and room temperature impact energy is very low. And when the room temperature impact energy is very low, railways face a problem because during handling of these rails, when they handle the rail before laying the track, lots of cracks form under the material fails because it has poor Charpy impact energy at room temperature. So this issue we tried to, and also in addition, it has high wear rate, but it is not too high because its strength is low. It has limited load carrying capacity. Carrying capacity of load of this material is not very high, and in modern times, because huge tonnages of freight are carried by railways, we need to have rail tracks which have superior load carrying capacity. Therefore, we decided to design a new alloy based on carbide-free benitic microstructure. We started doing our calculations with this composition, and we calculated the GTT diagram. We studied the effect of various alloying elements on hardenability. I think this is all published, so if one is interested in detail, they can get it from it. We also studied the effect of different alloying elements on T0 concentration, which I just described, and a stability index of austenite in terms of difference in the free energy of austenite of the average carbon content and the free energy of austenite at the T0 point. So this is the last plot here is a measure of stability of austenite in terms of free energies. Also, cement, we investigated certain aspects of cementite. When would cementite precipitate? Because barite transformation is limited by T0 point, which means the transformation stops when the austenite carbon content reaches T0 value. And when this T0 value exceeds the extrapolated ACM line, cementite precipitation will take place. And if cementite precipitation takes place, cementite is a brittle phase, it will impair the toughness of the material. Therefore, the idea is to design a composition which will suppress cementite precipitation. So here you can note this. So this is the critical temperature composition combination. If we are on the right hand side of this point, we are the carbon content of T0 is more than extrapolated ACM line. Obviously cementite will precipitate. And if we are on the left hand side of this dashed line, which is extrapolated ACM line, which means austenite is not yet completely saturated with carbon with respect to cementite precipitation. Therefore, cementite precipitation will not take place. So we studied the effect of different alloying elements. What do we see? That most of the alloying elements have hardly any effect on cementite precipitation or this critical value, whereas this is the effect of mm, uh, 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 at 550 degrees centigrade, and one can see that silicon has significant amount effect on shifting the ACM line towards higher carbon concentration, which means austenite is able to tolerate more carbon before it becomes ripe for cementite precipitation. Once again, the effect of different silicon concentration is shown here, and one can see that if there is 0% cementite, if you are below this line, below this particular line, then let me get the pointer. If you are below this line for a particular composition, cementite precipitation will take place. If you are above this line, there will be no cementite precipitation, and one can therefore decide the temperature combinations. Here you can see if we add 1.5% silicon, which is the topmost line here, cementite precipitation would become possible above 366 degrees centigrades. However, these calculations are based on thermodynamics only, but kinetics also plays a role. And here, what is shown here is solubility of silicon in cementite and effect. So you can see silicon has hardly any cementite solubility at 366 degrees centigrade, which means cementite precipitation can be suppressed completely by addition of silicon. And it will not precipitate even at 360 degrees, 6 degrees centigrade because of thermodynamic and kinetic considerations. We used also simple models to be able to predict the strength of bainite depending on the lathe size and dislocation density and so on and so forth. So therefore, the effect of different alloying elements is summarized in this slide. And looking at it, the most optimum combination that will give us the desired properties is listed in the last column. So once through these studies, we shortlisted a few selected compositions for further experimental work. So, and one of those, we then calculated the CCT diagram for that composition, or all those compositions. Only a typical calculation is given here. You can see that the lines, continuous lines, are the CCT diagrams calculated from a software called JMAT Pro, whereas these points that you see here are experimentally measured values, and more or less there is a good match between the experimentally determined transformation temperatures and those predicted by the CCT curve. So one can see that if the cooling rate for this particular steel exceeds 1 degree centigrade per second, then we will be able to get benite. And we did actually some experiment, we did some measurements. The rails are made by Bhilai Steel Plant in their rail rolling mill. One of my students went there and measured the cooling rate of rails after rolling, and he found out that the cooling rate lies in the range of 1 degree centigrade to 2 degree centigrade per second. Therefore, we designed it in such a way that during continuous cooling itself, we get the benetic structure, which is what is confirmed by the calculation and experimental measurements. If the cooling rate is more, let's say 10 degrees centigrade per second, then we will get martensite for the composition for which this CCT diagram is shown. So based on some basic calculations, we designed a composition. We calculated the CCT diagrams, confirmed the CCT diagram by experimental measurements, and we found out that in the cooling rate range, range that is appropriate for benite rail steel production, we will obtain a benite microstructure in this steel. So once we did all these studies, we made a steel in our laboratory using air induction furnace. A typical range of composition is given here. We made three alloys actually, and after cooling at different rates, one can see that SEM picture which clearly shows that we get benitic microstructure. Some more detailed studies were done to measure the benitic ferrite lat thickness, etc., and confirm the presence of retained austenite in the microstructure. So the details of microstructure are given. I mean, we quantified it. The student actually quantified it for all the three experimental steels that were made in lab. So one can see the amount of retained austenite. That is the first row here in the three steels. Its carbon content ratio of bulk and film austenite, their MS temperature, so the volume fraction of benitic ferrite and martensite, etc. To microstructural characterization was done in quite a bit of detail. And one I highlight the amount of retained austenite in the three steels and the carbon content of benitic ferrite. One can see it is not quite low; it is about zero point 0.1. And then obviously we did tensile test of this material after processing, after rolling and cooling, etc. You can see that the last one is pearlitic steel. It has a UIS in the YS was found to be greater than 460 MPa. But the rail steels, because there are three varieties, the range is given. It ranged well above the strength of Parleti grade. UTS was significantly better than 880 MPa, and even though there was an increase in strength, the ductility was superior. Normally, we believe that if strength increases, ductility decreases. In this case, because we have changed the essential character of the microstructure, pearlite grade gives about 10% total elongation, but carbide-free benite grade has given us up to 17% total elongation at a higher strength, and hardness is also higher. One can see hardness is very high compared with the pearlite grade. Apart from this, room temperature Charpy energy value is also about 2.5 times greater than the Charpy energy of pearlitic grade. We tried to measure K1C values also, but we could not produce in sufficiently large thickness to be able to measure K1C. Therefore, KQ value is reported, and in terms of that value, it's also the experimental steels are seen to be superior to pearlitic grades. So for rail steels, sliding wear is very important, because when trains run over it, there is sliding between rail wheel and the track, and it tends to wear off. For pearlite grill, there is a problem of formation of white layer, etc. Those who are interested can explore that aspect. But in this case, we compared the sliding wear behavior of benite grill and pearlite grill. These experiments were done in R&D center of railways, which is there in Lucknow. So some typical conditions in which the test was done is listed here. Sleep is about 10%, and wear test was done in dry air atmosphere at certain loads and RPM values. The result is important. Result is plotted in terms of loss of weight. So if the loss of weight is greater, which means it has inferior wear resistance. If wear resistance is more, obviously the loss of weight will be less. And also we are plotting the initial hardness of the material, hardness in the beginning of the wear test or of the as produced material. And it is obvious that PR is the pearlite grade. Steel 1 and steel A1 are two varieties of experimental carbide-free benedict steels. And it is obvious that the experimental steels have superior wear resistance. Also, we believe that if you use benedict rail steel, then wheel wear is also reduced compared with the pearlite grade. We looked at the wear track also. It has wear tracks were characterized, and from that point of view also carbide free benedict steels appear to have greater wear resistance than pearlitic steels. The reason we believe is because of the crack propagation path, because there is retained austenite in the material. It transforms during wear to martensite, and therefore it has superior wear properties. So films of retained austenite that are present in the benedict steel is beneficial for wear resistance because they reduce the crack tip in stress intensity factor via the trip effect. A second example of Benedict rail steel could be in the forged automotive components. You know, automotive components in their powertrain has many components that are produced by typically forging through forging route. After forging, the material is hardened and then it is tempered. However, during hardening process, as you will all be aware, that there is distortion of this component and there is a possibility that it might crack because these are medium carbon steels, and during hardening process it is such that it causes warping or distortion of the component, and there is a possibility of crack. And to take care of this, after hardening and temporary treatment, material has to be straightened, straightening has to be done, and once it is straightened there are some stresses that are introduced. Therefore, to get rid of those stresses, stress relieving annealing is required. So you can see that it has a very long cycle, and this is energy consuming because one has to do hardening, tempering, stress relieving annealing. So it is energy consuming, time consuming, and it's a complicated process. So it is maybe possible that if you can replace this normal quenched and tempered steels with benedict steels, which will be produced in such a way that immediately after forging we cool it in a controlled way in air, and at room temperature we get benedict microstructure. It is possible that we will get the correct combination of properties which is equivalent to the properties of the quenched and tempered microstructure. So this is a work which we are still doing, and so that is another example of 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 application of benedict steels. Two more applications, or one more application perhaps I will show later on if time permits. So because the essence of these three examples that I have given you till this point is benite transformation, let me summarize the transformation very quickly. So all of you are aware of benite, where it forms. It forms at an intermediate temperature, below the temperature at which perlite forms, but it forms at temperatures above the temperature at which martensite forms. So it is an intermediate product, right? And we believe it forms by a displacement mechanism. A typical structure is shown here. On top is the optical micrograph of this material, where you'll see plates of benite, these dark plates of benite. Just give me a minute. Just give me a minute. So, so these are plates of benite, but what appears like a plate on an optical microscopic structure, you can see the micron marker here. When looked at higher magnification or higher resolution, it turns out that it consists of a sheaf-like structure where white regions are benedict ferrite and dark regions, in this case, are retained austenite. It could have been cementite as well, right? So in this case, it is carbide-free benedict steel, which is consisting of a sheaf. Sheaf comprises of platelets of ferrite, which are white regions, and and the black regions are the austenite regions or film austenite regions that separate the ferritic plates. And in the microstructure, there will be several such sheaves originating from austenite grain boundaries. And in between sheaves, we could have blocky austenite also. So that is the typical microstructure. So when ferrite grows, if the ferrite part of benite grows, it causes an invariant plane strain shape deformation, resulting in the kind of surface relief that you see here, which is a result of an atomic force microscopy structure. We can see the complete, you can see the relief on the surface. This was a pre-polished surface before transformation to benite, but after transformation to benite, it causes a surface relief because of the shear nature of the transformation. So once again, these measurements across the plates, you can see that this is the strain caused by the shape deformation of benitic ferrite. And because of this shape deformation, the neighboring austenite region undergoes a small plastic deformation. And this is a schematic representation of the transformation. So benitic ferrite first nucleates on austenite grain boundaries. So plate grows with complete supersaturation. It grows by a shear mechanism or displacive mechanism. Therefore, it is associated with some strain. And to accommodate that strain, the parent austenite phase, because it is at a higher temperature compared with martensite, undergoes plastic deformation. So if the parent austenite phase in the neighborhood of a growing plate undergoes plastic deformation, lots of dislocation debris are generated, which interfere with the growth of the glycine interface. Therefore, plates stop growing. So each plate stops growing prematurely because of the strain generated by the growth. And then new plates nucleate at the tip of old ones, and then it grows to certain extent, and then it stops. And then new plate will grow further at the tip of old ones, and then it can grow laterally also. In this way, we get a sheaf-like structure. So at low magnification, this entire sheaf that I am enclosing here now would appear as one plate. But looked at higher magnification, and I have shown you in the beginning of this section itself, that it consists of these platelets. These are platelets of ferrite, which initially when it forms is completely supersaturated with carbon and other alloying elements, but afterwards, because the transformation temperature is higher than martensite temperature, the carbon, at least the carbon atom, because it has higher diffusivity, will diffuse out and go to the neighboring austenite region, from which, if the composition is right, it can precipitate out as carbide. If not, then austenite will remain stable. This film will be of austenite only. So thermodynamically, we can understand that, let's say we are transforming an austenite of this composition, the first bigger arrow one. So austenite transforms to ferrite, and because the transformation mechanism is displacive, ferrite has the same composition as austenite from which it forms. Therefore, this is the total free energy of transformation of the first set of plates. So after the plates formed, as I said, it stops when after it has consumed only a limited amount of austenite, because of the strain that is generated and because of the dislocations that are generated, which immobilize the glycine interface. So once splits grow very rapidly and stop, it releases its excess carbon into neighboring austenite. So austenite gets enriched with carbon. So it has grown, a plate has grown, it stops, carbon is released, excess carbon is released into parent austenite. So when the next set of plate therefore forms, because austenite is enriched, it has lower driving force for growth. And this is how it continues until you reach this point, which is known as the T0 point. Beyond this, if carbon content increases further, then austenite cannot transform to ferrite of the same composition, because that is a thermodynamic impossibility. Any phase cannot transform from a lower free energy state to a higher free energy state. Therefore, once the austenite reaches T0 composition, and austenite is able to retain this carbon, because carbide precipitation is suppressed by adding silicon or other alloying elements like aluminium, then austenite will continue to have a composition given by T0 point here, which is where I am pointing out, and it will not be able to transform further to ferrite, because that is a thermodynamic impossibility. Therefore, this point is the limit at which transformation will progress at the temperature T1. So now if you can take this T1 and plot the locus of this point as a function of carbon concentration, we get what is known as the T0 point. Right, this is what is shown here. This is where the transformation stops. T0 prime simply indicates when we add to this the strain energy of transformation. So we get this particular line where strain energy is added. So the locus of this point is the T0 prime line shown in this plot as well as this plot. So that is the thermodynamic limit beyond which transformation cannot happen if carbide precipitation is suppressed. If carbides precipitate out of cementite, for example, if its carbon content is more than ACM at the temperature concerned, then carbide can precipitate out if kinetics also permit. Then its supersaturation would be lost, then it can go back to lower concentration. But if carbide precipitation is suppressed, then austenite carbon content will be given by T0 or T0 prime line when bainite transformation stops. So this is what is known as incomplete reaction phenomena. Austenite cannot be consumed entirely by bainite if carbide precipitation is suppressed. And there is experimental evidence to show, you can see as the temperature decreases, because the T0 line has a negative slope, like A3 line on iron carbon diagram. Therefore, amount of bainite increases as the transformation temperature decreases, and it stops along the T0 line. Whereas A3 line is here. A3 line is here. So you can see the transformation stops well before austenite composition reaches the equilibrium composition given by this point. The locus of this point is obviously A3 here. So that is why we call this transformation is incomplete, in the sense because the transformation stops even before austenite carbon has reached the A3 temperature. Now, how do we study phase transformation in steels? Phase transformation in steels can very well be studied by equipment called dilatometer. It measures change in length or change in volume as the material is heated or cooled. And if there is a transformation, and if the transformation is associated with a volume change, it can be picked up as and when the transformation happens. So it can pick up the transformation online as it happens. We don't have to see the transformation after a particular heat treatment, and we don't have to go to microstructure to understand it. Of course, eventually we have to do the microstructure, but at least that some transformation is taking place can be detected online even as the material is heated or cooled. So this is the equipment that we have, where Sadri Party has extensively used for her studies. So it has an induction coil in which we place the sample, and the sample is heated using induction coil, and there is an LVDT here which detects the length change with heating or with transformation as well. So this is the typical sample that we use for these kinds of test, which can be and or entire thermal cycle, heating, cooling, or holding at a particular temperature, can be computer or program controlled. So what a typical output is given here, where you can see if you do heating part of an interstitial free steel or a low carbon steel or a medium carbon steel, this is the thermal expansion due to heating. But when the room temperature ferrite transforms into austenite, as you know, BCC is transforming to FCC, which is more close packed. So there is a volume contraction because of transformation. So this part indicates the transformation, and once the transformation is complete, here we have completely austenitic structure, and if you continue to heat, then this is the thermal expansion of austenite, whereas this is the thermal expansion of ferrite. So in this way, we can simply detect the transformation start and finish temperatures and plot them on a CCT diagram. One such CCT diagrams of one of our experimental triped steel is shown. So you can see that if at different cooling rates, how the different phases is formed, and if the cooling rate is too high, we do not get ferrite bainite, we directly get martensite. So this we use extensively to understand transformation. So one more example is given here. What happens to a normal low carbon steel, which comprises at room temperature of ferrite and perlite, a very small amount of perlite. So typically, perhaps this would have about 0.1 weight% carbon. So this steel is heated. So you can see when you heat this steel, there is thermal expansion. What we detected unusually is there is a status here. Even though we are heating it, it does not expand. So something is happening here. And once this is over, it again starts to heat up, undergoes thermal expansion. Once ferrite begins to transform to austenite, there is a contraction. Once the transformation of ferrite to austenite is complete, we have 100% austenite at this point. If you continue to heat, the austenite undergoes thermal expansion. That is very simple. But this was kind of, we first thought that there is a glitch in the equipment. It is, we are just getting some noise. But then we investigated it further by modeling it, and of course, what we can also do is we can take the slope of this line with respect to temperature. We can take the slope of this and plot, and it clearly shows. So this is the raw dilatometric curve, and one can plot the slope. You can see this slope is constant here, so this value is the thermal expansion coefficient of a ferrite and a small amount of perlite, and there the slope decreases. So this will help, this helps us in detecting the transformation very easily. Some more examples of CCT diagrams of two more experimental varieties are shown here. And the corresponding microstructure. This is, for example, a phosphorus containing steel. We do dilatometry experiments to first detect the transformation temperatures, which are plotted in the form of a CCT curve. And once this is done, we have to investigate the microstructure at the end of the day to understand that at particular cooling rates, what is the microstructure that is formed. And we can take the hardness also, so that will complete the set of a CCT diagram. So as I was saying, that we studied the formation of ferrite, formation of austenite during heating of a ferrite perlite structure. So you can see that this is the this is the straight line of heating of ferrite perlite. So that corresponds to thermal expansion of ferrite and perlite. And this was a somewhat new thing that we noticed, which we initially thought was just a noise in the data. This is well known that there is a contraction because of austenite formation. So we investigated it, we modeled it, we developed a simple model. Normally what happens is, normally people use this kind of dilatometric curve to detect the transformation start and transformation finish temperatures only. Or we can do a semi-quantitative analysis. By this lever rule kind of work can be done to quantify the amount of parent phase and the product phase at any temperature. But that is a very crude way of doing it. We developed a method which is much more rigorous and based on how transformation happens. So we studied the transformation of ferrite at low temperatures to austenite during heating, or transformation of austenite to ferrite or martensite or bainite during cooling. So normally length change, which is one third of the volume change, and we assume it to be isotropic. So length change is a function of lattice parameter of the phase is concerned and their thermal expansion coefficient. If there is no change, if there is no phase transformation, then simply the slope is the thermal expansion coefficient. Now, phase fractions, if there is only thermal expansions, phase fractions do not change. But if there is a transformation, phase fraction changes. At the same time, during heating or cooling, the lattice parameter changes. Lattice parameter of the phase at any phase is a function of temperature and the thermal expansion coefficient of that particular phase, whether it is ferrite or austenite. And the room temperature lattice parameter of any phase will be the lattice parameter of iron plus the lattice parameter of other alloying elements. Use this kind of equation to work out the lattice parameter of the base material, which has the effect of other alloying elements also. X there represents the mole fraction of, or weight percent of alloying of different alloying elements, and how they affect how they affect the thermal lattice parameter. There is a coefficient C, and X is the mole fraction. At any point, sum total of all the phases must be 1, and Lever law will apply, which means mass balance will apply. Fraction of any phase and its composition must add up to the overall composition. So this is then the expanded equation, where you'll see the length change that we detect experimentally is a function of fraction of phases, composition of phases, lattice parameter at room temperature, thermal expansion coefficient, and temperature. So we wrote this model, and then we iteratively fitted the experimentally calculated dilatation curve with we iteratively calculated the dilatation curve and compared it with the experimental dilatation curve to find out the volume fraction of phases. So this is an analysis method that has been done. We calculate the dilatation curve, compare it with experimental dilatation curve, and then you update the parameters, which are the thermal expansion coefficient, the fraction of phases, and the carbon content. For this analysis, we assume that only carbon concentration changes. Other alloying elements do not partition between the parent phase and the product phase. This situation is called as a para-equilibrium transformation. So we assume that all transformations take place under para-equilibrium condition, and therefore we can solve these equations iteratively to find out the phase fractions. So we applied this first of all to Martensite transformation. One can see that for a particular experimental steel, which I have shown earlier also. Actually this is for two experimental steels, the aluminum steel and silicon steel. We cooled it from austenite region at a rapid rate to get martensite. So at least we can detect the MS and MF temperatures for both the steels. And room temperature microstructure is fully martensitic, maybe with a small amount of retained austenite. And I must point out that we began with this transformation because austenite, this transformation is the simplest one because of the fact that the parent phase and the product phase have the same composition. So we have one less variable in the set of equations that I showed you. We have one less variable, parent phase and the product phase have the same composition in this case. Therefore, it becomes easy to solve those equations. So therefore, we solved it to find out the fraction of phases. Normally, it is believed that C by A ratio of martensite is not a function of the concentration of other substitutional annoying element. So on the left hand side, you see the experimental curve. On the right hand side, experimental dilatation curve is superimposed with the calculated curve, where we ignored the effect of substitutional alloying elements on martensite transformation or its lattice parameters. And then one can see that the match is not very good. But if we is there is someone trying to say something? Hello.
No, sir, you can continue.
Okay. So when we added the effect of alloying elements on the lattice parameters of martensite, we obtained a much better fit, and that is how we know that the method is robust. And of course, once we know we did this method, then we calculated the fraction of martensite as a function of degree of supercooling below the MS temperature. We also calculated by the normal lever rule method in this case because they both should give the same result. So we can see there is a very good match. And then there are several kinetic models for martensite transformation. We compared our results of progress of martensite transformation as a function of temperature below ms with most of these models that are available, and one can see that the match is not very good. Therefore, we proposed this kind of model for martensite transformation where n value would be a function of alloying elements. We also then did X-ray experiments to find out what is the lattice parameter ratio, C by A ratio of martensite, and one can see that the ratio that we got from our experimental results matches very well with the most recent value of C by A ratio, which is represented by this equation due to Lee and co-workers who published this in 2017. So this is their relationship that C by A ratio should be 1.1 plus 0.031 into 8% of carbon, and our values are very close to this equation, as you can see from this. So this is the C by A ratio that is expected from dilatation curve. This is the C by A ratio that we get from dilatation curve. This is the C by A ratio that we get from X-ray diffraction experiments, which means there is a very good match. And this is the theoretical C by A ratio for the steel. So we know that our method is good. We did some further analysis to understand the effect of for example, aluminium on the lattice parameter, because this is not known or not reported in literature. Therefore, we carried this analysis further to understand that. This work is published. So now, in this case, of course, we have an indirect verification of the fact that our method is working well, but there is no direct evidence. Direct evidence can be obtained only when we take a steel which we transform to ferrite at an intercritical temperature between A3 and A1 temperature, transform to ferrite at a given temperature for certain duration of time. And then if you quench from that point, then the untransformed austenite will transform to martensite. And then we can see the microstructure in terms and quantify it in terms of the volume fraction of ferrite and martensite. So you can see one such treatment and the result is shown here. Here we can clearly see how much of ferrite has formed when a material is treated at a given temperature for a certain duration of time. And the typical dilatation curve that we will get is that we cool from austenite. During ferrite transformation, austenite will transform to ferrite, and in the process, austenite will get enriched with carbon. So at this point, austenite carbon content would have increased corresponding to to a certain fraction of ferrite that forms at the temperature. And this austenite, when quenched further, cooled further, will transform to martensite at a lower temperature. And the MS temperature that we see here would correspond to the carbon content of austenite that was present at the end of intercritical treatment. Same thing is shown here in terms of relative length change and temperature data. So here, as we are cooling austenite, there is thermal contraction. At this point, austenite transforms to ferrite and leaving some amount of austenite with higher carbon, which upon further cooling transforms to martensite. So this MS temperature is a signature of the carbon content of austenite that is present here. And now we can clearly see the microstructure as to what is the amount of ferrite. So we used our method to calculate the amount of ferrite. We saw the amount of ferrite directly from the microstructures like the ones that I showed you, and we did a comparison. And comparison is very good. As you can see, the ferrite fraction obtained from direct optical microstructure analysis matches very well with the ferrite fraction that we calculated by applying our method of analysis of dilatation curve. So you can see there is a clear one-to-one match. And MS temperature also that we calculate, it matches very well with the experimental MS curve. So summary of this part of is that we can do much more detailed quantitative analysis of dilatation curve, and from which we can get volume fraction of phases as a function of temperature or time, in addition to the fact that we also get the transformation start and finish temperature. For the martensite transformation, we also concluded that it is important to include the effect of substitutional alloying elements on the lattice parameters, and we use this technique to determine the lattice parameter coefficient of aluminium, how aluminium affects the lattice parameters of austenite and ferrite. Okay, so can we move over? Do we have time to move over to the?
Yes, sir.
Okay. So now, after having gained some confidence in our method, we applied the same method to understand Benite transformation. And I would focus it here because that has been the subject of my talk for today. So once again, like martensite, we did Benite transformation. Also, we cooled at a continuous rate at such rates that where we do not get ferrite perlite, neither we got martensite, we get Benite. So these are results at intermediate cooling rates where austenite transforms to Benite. Some amount of austenite, as I said, Benite transformation is incomplete in some cases where the austenite that remains untransformed after the Benite transformation may transform to martensite further if the carbon content of austenite is such that its MS temperature is above room temperature. However, if the carbon content of austenite at this point is so high that MS temperature is below room temperature, then we cannot detect it by this method. So this we started with an alloy containing 0.28% carbon and did diretometric study to understand the Benite transformation. Now we fitted our calculated dilatation curve to the experimental dilatation curve, assuming that benitic ferrite has body-centered cubic structure and its carbon content is negligibly small, because that is what we know till this point, that ferrite has very limited solubility of carbon. And then we say that the match is not very good, and not only that, it gives some ridiculous results in the sense that it says that austenite carbon content can go up to 9 or 10 atom 9 or 10%, which is ridiculous because we know austenite also has limited solubility of carbon. So this obviously is the incorrect situation. We repeated the calculation by assuming that benedict ferrite is body centered cubic, but we allowed its carbon content to vary, and we calculated the carbon content by assuming para-equilibrium transformation of austenite to benite. The fit improves significantly, but the best fit is obtained when we assume that the benedict ferrite had body-centered tetragonal structure. So that gives us the best fit, and we believe that this to be true, right? And from there, then we can then during the transformation in this range, when we calculated how the amount of benite changes with temperature or amount of austenite changes with temperature. So as the transformation progresses, the amount of bainite increases. As the material cools, amount of bainite increases, amount of austenite decreases. We also calculated the carbon content of austenite by using our method, right? And once we got bainite, we can use X-ray diffraction directly to calculate the C by A ratio. And from this, what we see that the X-ray results and the results that we obtain from analysis of dilatometry, they are very close. So one can see X-rays tells us that benedict ferrite has about 0.2% carbon, whereas dilatometry analysis says it has 0.188% carbon. So there is a good match. Remember, what we are saying is Benedict ferrite is tetragonal, not body-centered cubic. It has body-centered tetragonal structure, and its carbon content is almost as high as the carbon content of parent austenite from which it has formed. That was zero point 0.2. Here, Benedict ferrite has 0.18% carbon, which is kind of surprising because normally it is believed that Benedict ferrite would also, or ferrite in general, has very small solubility of carbon. So this work was taken up by my friends in Bhava Atomic Research Center, Harish and Suman Yogi. They used our method of dilatometry analysis further and went into much more detailed analysis of benite transformation, and they came to the conclusion that in their steel, as I said in the beginning while I was explaining benite transformation, that retained austenite that we see in Benedict steels has two morphologies. Film austenite between Benedict ferrite subplates or platelets, and bulk austenite or blocky austenite between sieves of benite. So austenite within a sieve between ferrite subplates, and bulk austenite between different sieves. And it was known even before this study, it was known for a long time that film austenite has higher carbon than bulk or blocky austenite. And he, for the first time, using the method that I have just described you, he for the first time quantified that the film austenite has twice as much carbon as the bulk austenite. So this is a further detail that has been obtained. So what do we conclude for this study? Crystal structure of Benedict ferrite could be body-centered tetragonal. I say could be because it need not be body-centered tetragonal in all the cases, as I will now explain afterwards. So it could be Benedict body-centered tetragonal in some cases. It contains higher carbon than is usually believed. It has 0.18% carbon. Obviously, this clearly shows that the mechanism of transformation is displacive. And film austenite has twice as much carbon as the blocky austenite in Benedict microstructure. So Dr. Ipsa, please let me know when is time to end because my talk is in several modules. I can end. Just give me 5 minutes of notice and I will end. Right. So with this, we did some ice. Right.
Yes, sir. Yes, sir. Now it's time. Time is there. You can explain.
So whenever you just give me 5 minutes of notice, and I will be able to wind it up.
Okay. Okay, sir.
Okay. So isothermal, we did on the same steel for which I showed you the results of continuous cooling transformation. We did IBD3. Oh, no, we did some more experiments to understand the effect of prior benite. Before we go to other, we did isothermal benite transformation. This is on a different variety of steels. Sorry, I made a mistake. So we did isothermal transformation in one step. We did isothermal transformation in two stages, where a transformation at 430 degrees centigrade was preceded by a small holding period of 50 seconds at 480 degrees centigrade. So a small amount of bainite will form at 480 degrees centigrade, and then we wanted to study how this bainite will affect its transformation further at a lower temperature. So we did more, and I think I will. You can go through publications. I will come to the main conclusion only. So the conclusion is the total amount of benite is less in the two-step process than in a single-step process. So it shows a kind of thermal stabilization that is very well known for martensite transformation. Martensite shows thermal stabilization. Similarly, benite also shows thermal stabilization. We did several such experiments at two-stage experiments and compared them with single-stage experiments and quantified the microstructure in terms of benitic ferrite content and martensite content. We also studied the MS temperature of austenite after benite transformation. All these leads to the conclusion that austenite shows thermal stabilization during benite transformation also, which is similar to the thermal stabilization that is observed for martensite transformation. And a consequence of that is that size additivity principle that is normally applied for transformations under continuous cooling situations to ferrite and pearlite may not be applicable for benite transformation. We did some more analysis of kinetics of benite transformation, so that those are matters of details. So if you are interested, you can look into those publications which are listed at the end. We also studied the effect of austenite grain size on kinetics of benite transformation. And so we did this at four austenitizing temperatures, which lead to a gradual increase in the grain size of austenite, and then transformed them. You can see that there is a as the austenitization temperature is increasing, there is a gradual increase in the grain size of austenite. And what do we see? We see that the higher the oxidizing temperature or coarser the grains, we get greater amount of benite, and the kinetics become faster. We analyze this further. So kinetics become faster as the grain size increases and the volume fraction of benite also increases. There are very good reasons for showing such behavior is because plates have more space to grow, therefore the volume fraction increases. One can see that the average plate thickness increases with austenite grain size or the austenitizing temperature. So as I said, we did calculations. We did kinetic calculation to understand how nucleus and site density changes with grains as the grain size as the austenite grains become bigger. The number of nucleus and sites reduce. Therefore, autocatalysis factor plays a better role. Therefore, the kinetics improve and the volume fraction of bainite also increases. So that's one aspect of isothermal bainite transformation, which gives us some clues to how different microstructure parameters play a role. We then go on to study another aspect of bainite transformation to understand the mechanism of transformation in a better way. So we started with two steels. As you can see, there are results for two steels here, aluminum steel and silicon steels, which I had already discussed earlier. So we gave two kinds of thermal treatment to these steels. After austenitizing at 1050 degrees centigrade, we austempered it at some temperature, I think 430 or 450 degrees centigrade directly. So green line is direct austempering treatment, where the parent austenite that undergoes bainite transformation has the same carbon content as the austenite carbon here, right? Which is obvious. In a second variant of this treatment, what we did is after doing the same austenitization, we held it in the intercritical temperature region. By intercritical, I mean that at any temperature between A3 and A1 temperature. We call this FBT treatment, where bainite transformation is preceded by ferrite transformation. So here some amount of ferrite will form, and as some amount of ferrite forms, then austenite carbon content will increase, and therefore when this material is subjected to bainite transformation, even though the transformation temperature is the same, parent austenite carbon content, the carbon content of parent austenite that transforms to bainite is more than the parent austenite carbon content in this case, which is direct BT treatment. And I think we chose a temperature where we formed 50% ferrite. So in the case of red dashed lines, the parent austenite has double the carbon of austenite of the normal BT temperature. So you can see we cooled it, we obtained bainite transformation at the IBT temperature without any ferrite transformation. In this case, there is a two-stage treatment where some amount of ferrite forms, about 50% ferrite forms at this temperature, and then austenite gets enriched with carbon, and then it is subjected to austempering treatment for bainite formation at lower temperatures. So one can see the results in terms of how the dilatation curve changes with temperature and time. So obviously, in the first case, in the BT treatment, the microstructure is all bainitic because we did direct austempering here. Maybe there is some amount of austenite martensite, but the major part of the microstructure is bainite. In the second case, when the two-stage treatment, the FBT treatment, we allowed 50% ferrite transformation before bainite transformation. So as a whole, these bainites will have higher carbon than in these cases, right? And then we did some more analysis, but that may not be so relevant for this lecture. So what do we see? After the transformation, we measured the carbon content of austenite and carbon content of benitic ferrite. For the single stage BT treatment, carbon content of benitic ferrite is low as expected, and carbon content of austenite is higher, and it follows the T0 curve, as I have explained that bainite transformation stops when it hits the T0 curve. So this is the composition, these are the compositions of austenite when bainite transformation comes to a halt, and it follows exactly, very closely it follows the T0 curve for one stage transformation. For the two stage transformation, however, results, the trend is similar, but there are significant differences. What are the differences? Carbon content of benitic ferrite is far higher. Here it was very low. Here carbon content of benitic ferrite is high. At the same time, carbon content of austenite when the bainite transformation halts is higher than the calculated T0 line. So it is higher. So you see there are two lines, one for the silicon steel, one for aluminum steel. So there are two results. Bainitic ferrite has higher carbon, and carbon content of austenite when the transformation comes to a stop is higher than the T0 curve. Right? So these two are the main results. And we then thought why it is happening. We went to literature. We found out that literature also has reports, similar reports, where they say that transformation takes place beyond T0 also. So carbon content of austenite is shown beyond T0. So there are quite a few results along the similar lines. In fact, Pereloma has summarized this. Not this. This is a summary of results which also show that benitic ferrite has higher carbon, higher than zero point 0 or 0 carbon. It has significant amount of carbon in a range of steel. So both the types of results are also available in literature. In fact, our own work long ago in 2008, we did simple analysis using microstructural parameters. We also came to the same conclusion that it appeared to us that the benitic ferrite has higher carbon than is usually believed. Usually, we believe that ferrite has very small solubility of carbon, but our results back in 2008 also showed that it has higher carbon. So normally, people in the earlier days, what people thought is because these are the carbons that are located as defects. They are not in solution because the carbon are trapped by defects, and therefore we track extra carbon in bainitic ferrite because these are carbon that are trapped at different defects like dislocation, etc. But afterwards, very high resolution measurements using atom probe tomography or 3D atom probe tomography were done away from this defects region, and there also they saw that carbon content of bainitic ferrite is indeed a higher. This is the carbon that remains in solution away from defects. So it is now generally expected that bainitic ferrite, the solubility of carbon in bainitic ferrite is higher than we expect from an equilibrium between BCC ferrite and FCC austenite. So solubility of carbon in ferrite in equilibrium with austenite is higher than expected from para equilibrium between BCC and FCC. So that is the major conclusion based on this work and earlier work also. So the reason for this is we tried to investigate, and we saw that the underlying reason is the mechanism of transformation, which is shear. So this you have all seen that how Bain strain model works. The Bain strain model works in this way, which I think all of you are aware. I will not go into that. But important point from this work to note is that when you see this model, octahedral voids are only at one of the three sublattices of octahedral voids here. And when some of these sites are occupied by carbon, then Bain strain is somewhat different, and therefore it results in a tetragonal structure. And when this transfer, so the conclusion from here is that when supersaturated ferrite first forms from austenite by a shear mechanism, it is essentially tetragonal because all the carbon atoms settled on only one of the three sublattices of octahedral voids, only these octahedral voids, which result in a tetragonal structure. But what happens afterwards? Let's say after ferrite has formed as a result of shear transformation, what happens? If the temperature is high enough, these carbon atoms can go to other octahedral voids also, and then this will no longer remain tetragonal, it will become body-centered cubic. But if the temperature is lower than a particular temperature, a critical temperature, then carbon atoms will continue to remain ordered on this sublattice and will continue to see a tetragonal structure. So this analysis was the first time done by Zinner in 1948, and he did a simple model to calculate the ordering temperature, the temperature above which the carbon atoms will disorder to give a body-centered cubic structure. And if the transformation is, or if carbon ferrite containing excess carbon is below this temperature, it will become ordered on only one sublattice as shown here, and then we will get body-centered tetragonal structure. Of course, this calculation was done in 1948, so this is an old one. There are now some improved models. According to these improved models, if the transformation for room temperature transformations, if the carbon content of austenite is zero point 0.2 or less, so if you are on the upper side of these curves, there are three, the results from three models are shown here. If you are above this line, then we are above the ordering temperature. Carbon atoms will disorder on all sublattices of octahedral voids, and it will produce a body-centered cubic structure, which means that for room temperature, this dashed line is the room temperature. At If carbon content is about zero point 0.2 at room temperature, we should get a body-centered cubic ferrite or martensite. But if carbon content is more than zero point 0.2, then we are in this region, in the ordering region, where carbon atoms will continue to remain ordered on one sublattice, resulting in a tetragonal structure. So if the carbon content is more than zero point 0.2, only then we will see a tetragonal structure. And when we have tetragonal structure normally, so when we have tetragonal structure, we cannot apply the same thermodynamics as we apply for BCC material. This is Zhang and et al. In 2013, they did some DFT based calculation. They found out that free energy of solution of carbon in body centered tetragonal ferrite is 1000 joules per mole less than the free energy of solution of carbon in body centered cubic ferrite. And they use this value to recalculate iron carbon phase, these phase boundaries of iron carbon phase diagrams, which clearly show that this line, which is in the conventional iron carbon diagram, shifts to these dashed blue lines when ferrite is body centered tetragonal. So you see there is a significant increase in solubility of carbon in ferrite. These calculations were, of course, done for a particular carbon content, austenite having 1.3% carbon, having C by E ratio of 1.07. And if ferrite is tetragonal, they say that solubility of carbon in ferrite will be higher. And if it is a tetragonal structure, normally what we do, we consider equilibrium between BCC and FCC to understand austenite to ferrite transformation, and we can draw a common tangent, get the equilibrium compositions and so on and so forth. But now we are saying that ferrite could be body centered tetragonal at below certain temperature, it can undergo ordering and produce a tetragonal structure. So we have to correspondingly apply that thermodynamics. And as I said, if the carbon content is higher, then there is an additional free energy decrease if carbon continues to remain in solution in body centered tetragonal ferrite. So this line is therefore the free energy composition curve of body centered tetragonal ferrite. So if at this temperature carbon content is low, BCC has lower free energy, but if the carbon content is higher, body center tetragonal has lower free energy. So if that is the case, then if you now imagine a common tangent between austenite and body center tetragonal ferrite shown by the blue line, the point of tangency will change to higher carbon, which means that then we can very easily understand why ferrite contains higher carbon than in the case of a body-centered cubic structure. So if the structure of body center, if the crystal structure of body center of ferrite is body-centered tetragonal, it should have higher solubility of carbon in ferrite. At the same time, tangent point of tangency will shift towards right on the austenite side also, which means the T0 point will also shift towards right if the ferrite is tetragonal. Therefore, in this way, we can say that that is the reason why we have seen that ferrite carbon concentration
Sir,
yeah, so I will end here. This
okay,
is then a thermodynamic basis for understanding why ferrite showed higher carbon and why T0 curve appears to have been shifted towards higher carbon in the case of FBT treatment where austenite had higher carbon, which means the transformation was taking place below the Zener ordering temperature. Whereas when transformation was simply ostempering, one step ostempering treatment, because the carbon content was lower, the transformation was taking place above Zener ordering temperature. Therefore, we had cubic ferrite having lower solubility and carbon content of austenite follows the T0 curve. So then we did some calculation of free energy of transformation, and therefore we see that we have understood the evolution of microstructure in Benedict transformation is related to metric curve, and results show that body center ferrite could have a body center tetragonal structure with a higher solubility of carbon. We cannot say it's saturated, super saturated, because solubility limit itself increases when Benedict ferrite is tetragonal. I think I should end it here and leave some time for discussion.
so participants, you can unmute yourselves and ask questions. So there are a few questions from participants. What are the key microstructural features that distinguish carbide-free benitic steel from conventional benitic steel?
Conventional benitic steel can be classified into upper benite or lower benite. Both these varieties would have carbon. In the upper benite, carbide films will be observed between ferrite platelets. So if I can go back to this slide. If I can go back to this slide. Just give me a minute. So let me go to schematic diagram. Can it be seen? So
Yes,
it will
sir.
have carbides between ferrite platelets. That will be conventional benite. In case of lower benite, some carbides will be within ferrite plate itself, which I have not shown it here. So for lower benite, there will be carbide, epsilon carbide at about 55 degrees to the long axis of the ferrite plate. So that is the conventional benite, upper benite or lower benite. In case of carbide-free benite steel, these films will be untransformed austenite only. These will be untransformed austenite. There will be no carbide. And it will show T0, the austenite carbon content will follow the T0 or T0 prime line. Whereas in case of conventional benite, because carbon austenite, if carbides have precipitated from austenite, its carbon content will decrease and therefore transformation may continue until entire amount of austenite is consumed.
So next, why is the term prior benite used instead of upper benite?
Prior benite I used only in the context where we are studying transformations in two stages, right? Where we did some transformation before the main transformation to see whether prior transformation has any effect on subsequent transformation also, because that would have a bearing on how transformation progresses under continuous cooling situations. That is the only context in which I called prior benite in this case, right? Where
Yes, sir.
we transformed it partially to benite at 480 degrees centigrade for 50 seconds, and after that we did the main transformation at 430 for 10 minutes to see how this benite formed at a higher temperature affects the one at a lower temperature. So in this case I called it prior benite, otherwise it is upper and lower benite. That is, prior benite does not reflect any morphological variant of benite. It is just that in this case, to distinguish between these two benites, I have used this term. Done.
Any more questions? You can unmute yourselves.
Yeah, if you can unmute yourself, I think I can stop sharing, I suppose. Yeah, any questions? I'll be happy to answer. Otherwise, also you can write me afterwards. Or most of the publications are listed, if you can see through our publications.
If there are no more questions, then I would
Then I
like
think
to
I have to first
thank.
thank because I think I just presented it. I must thank everyone who did this work. So the work obviously is done by my students. I just happen to present it. So you can see, so they are the ones who contributed to this work. So all are our students. D. Harish is the BARC student who is doing whose work I presented in one slide. Right? So
Sir,
thank
yes.
them for this presentation. Okay.
Thank you,
Okay.
sir, for this in-depth knowledge on penite and martensite transformation. You have given the mechanisms and how you have fitted and how you have improved the model from the existing models. And the kinetics also you have discussed in details. Thank you, sir,
So
for
thank you.
keeping our
Thank,
invitation and joined us in this ATAL FTP program.
thank you for giving me this opportunity to share my work. So thank you. I can log off now, right?
Yes,
And
sir.
thank you the other organizers also. Thank you.
Yes.
Thank you, sir. Thank you.
Thank you, sir. So our next speaker, I think, we can wait for a few minutes. We can wait for a few minutes for next speaker to join.
Hello.
Good evening, sir.
Hello.
Good evening, sir. Good evening, sir.
Good evening.
So next speaker of our session is Dr. Suresh Tellu. Dr. Suresh, a metallurgist with over 13 years of industrial research and development experience. He began his career at Alpha Assembly Solution, where he was involved in the development of advanced soldering materials for electronic assembly applications. His experience gave him a strong foundation in material science, joining technologies, and process optimization. Subsequently, he transitioned into the welding filler metal development industry, where he has successfully led and contributed to several challenging projects aimed at developing next-generation welding consumables. His work has focused on innovation in material formulation, performance enhancement, and process improvement for a variety of welding applications. Over the course of his career, he has granted 4 patents and have authored several publications reflecting his commitment to advancing technology and creating practical high-performance solutions for industry needs. And he continued to passionate about research, innovation, and technology development in the field of materials joining. So let's welcome sir to our ATAL FDP online program. So you can start your presentation.
Thank you, Dr. Sir. I'll just I'm downloading my presentation. Just give me a second. Yes, it might take some time, but first I'll start with myself, Suresh. I've been working in welding industry from past maybe 10 years. Prior to that, I was with the soldering industry, where I have worked in developing joining materials of different, maybe different applications. And probably when I was invited by IPSA, I thought what to present to the team. I just thought maybe it's a completely uh, when we are studying, when we are doing a our academics, what we were exposed is different when we are coming to industry. What I thought is whatever I present, it should be helpful for people who are intended to take their career as part of in an industry. Probably in academic things are completely different. That is the reason. I thought I will make it presenting things which a what when we are for example different welding materials which will be used in welding industry, and also and its properties, and why particular welding materials will be used for a particular grade of steel or a different things. And at the end, I wanted to show some of the processes which will be used for manufacturing welding guns. That probably I'll take help from one of my friend, or one of my colleague is with me, is a Dr. Adarsh Prakash. He will also go through some of the slides. I'm just downloading. It's taking time. Try to share it. I just shared my screen. Probably my current organization is DNH who manufactures welding consumables. Maybe you might have heard of a different welding process, such as like SMAW, GMAW, GTAW, submerged arc flux welding, submerged arc welding. For all these things, DNS will manufacture different consumables. It's like a maybe I'll just like you might be knowing a different metals, ferrous, non-ferrous, ferrous, like maybe we can categorize material into different subcategories. What I will talk today is like a different steels and what type of different consumables will be used for welding with respect to welding. And also I'll show some of the processes which will be used for manufacturing those welding consumables. This is a simple, like everybody maybe, since everyone in the team, like everyone, the audience are like a metallurgist, they must be knowing with carbon, obviously, the strength will improve and elongation will reduce. Actually, in the welding field, we make this as like a broader thing. With like a, based on that, the welding consumable will be chosen. When it comes to, if you see, for example, if it is a low carbon thing, usually we use like a, where we use low carbon steels, we use industries such as like a general fabrications, transportation, and an energy segment. Why we use it? Like it is having a better ductility and better availability compared to strength and hardness. Strength and hardness is always less. And we use mostly in the transportation and energy segment, most of the cases. The same case in the medium carbon steel, if we see, mostly we will use it in a railways, okay, crankshafts, hand tools. And you could see a different properties with respect to why, because it's having a better strength, even though the ductility is less and the availability is slightly lower. Even the high carbon steels will be used in a cutting tools, dies, drill bits, nails, and so many other applications. Because like it is having a better strength and hardness, and it is also having a better wear resistance. And when it comes to low alloy steels, we will be having a like we can have up to add, we will categorize in the welding field like a low alloys, like up to 12% of alloying if we could add, we will categorize the low alloy steels. Here also high strength low alloy steels which contains chromium, nickel, moly, and creep resistant steels we usually call as a chrome moly steels. And low temperature services, we use a nickel as additive in order to have this thing. For weathering steels, we use a copper, chromium, nickel combination of steel so that it will have a better weathering. And for high strength steels, where we usually use it in energy segment transportations. Usually it contains a chromium, nickel, moly less than 12% in the weld. And these are the different properties I just listed for that. And when it comes to creep resistance, we will be having a chrome moly, which may be a 1% chromium, 0.5 or 9% chromium, like a chrome moly in a P91 will call, with the different additions of vanadium, tungsten, niobium, in order to have a creep resistance of the required properties, which will be used mostly for like a better weldability, which will be having a creep resistance property. It may also have a less, maybe there is a strength is medium, we can expect, and the ductility is lower, hardness will be lower. But because of the creep resistance, which will be used widely in the power generation and process industries, where like a mostly like a transportation and other process industries. And the low temperature service steels, where like a it will be used in the storage and the offshore applications. Usually low temperature service steels will be used, which will be like a maybe up to 196 degrees, for example, cryogenic applications, where we need a impact toughness up to 196 degrees. Okay. In those applications, we'll be using like a these type of steels. Whereas in a weathering steel, where like a bridges, buildings, railways, and all those things, we will be using consumable with a copper and chromium and nickel. Have like a better weather, like maybe protection from the atmospheric or harsh environmental conditions. When it comes to stainless steel, again, like it may be ferritic, martensitic, austenitic, duplex, and the precipitated hardened steels. And the ferritic steels, if you see, it may be like usually mostly it will be used in automobile, railway, and the home appliances. It will be. And it will be like maybe the 4 series, 409, 430 series will be used. It will be having a better oxidation resistance and the corrosion, the weldability, but the strength and ductility and hardness are relatable, less advanced. These are like a martensitic steels we will be calling as 410, 420. The composition, everybody aware. It will be used mostly in the power generation, home appliances, knives, surgical instruments. Okay. It will be the advantage with these things are high, very high strength it will be having. But like the weldability is a bit difficult because of the like a microstructural problems. And austenitic stainless steel will be having like a obviously like these are the most widely used steels in any industry. That is a 309, 316. Hello.
Light joy. Yes, I can continue.
Okay. 309, 316 and 347 are most widely used steels for welding, and they will be good because of its their better oxidation, corrosion, the weldability properties, even though they are slightly inferior with respect to strength and the hardness. Obviously, these steels will be used mostly in the like energy, textile plants, paper mills, and different like a kitchen furniture appliances, and duplex stainless steel. Mostly it will be used in like energy process industries, especially the textile plant, paper and pulp industries will be used. And the properties are like having a better corrosion, the weldability, strength and hardness compared to duct. But like it is like a very rarely or like applications are limited compared to previous. When it comes to aluminum alloy, there are different grades. Mostly it will be used in aerospace, automobile, structural, chip building, and other things. I'm not going in detail about it, but like these applications are like mostly in the automobile industry, mostly, and the defense, aerospace, and all those things. Aluminum alloys will be used. For those, the welding consumables are needed. Here, if you see like in a welding consumable wise, if you see like there is a handbook like a 5.1 time will call that like every welding consumable will be classified different category. If you see this, like if you see any welding consumable, you will see some sort of nomenclature. Every like a number or every digit here makes some sort of significance. For example, if it is SF5, SFA 5.18, if it is mentioned of welding consumable, it is for like a gas metal arc welding. Whereas like a 5.20, if it mentioned, it is for the flux core wise. If you see here, in the same way, for example, most widely used assembly consumable is, for example, this one you take. Here, E is nothing but an electrode. The first two digits are mentioned that like it will be like sometimes like these two are significance, the XX is signifies the strength. For example, strength of like a 700, if it is needed, then it will be written as a 7. One. Like you see here. And the next digit signifies the position. And the next digit signifies the electrode. Electrode coating means like a electrode like a in each welding consumable, like it will be having a different like a coating. For example, it may be a basic acidic based on the requirement. If we need like a better mechanical properties, then we have to go for a basic coating. If we need a better like a weldability, we have to go for a like acidic electrodes. Like that, like based on the application, it varies a lot. these things like probably like maybe general things. Probably we will go with some basic things. Till date, we have seen like a what like a for which applications, what type of steel, like for different steels and its applications in a welding field we have seen. Now we will try to see like a different welding consumable available in available in the market, and it's how it will be produced, that we will see. Others could please take it up.
Yeah. Good evening, everyone. I'm Adarsh. So we'll proceed with welding from here. So likewise, you have seen from sir, we have all the consumables. We have, I see, for all the welding of all the materials for any kind of manufacturing, we need some kind of joints to make a structure, and that joints are mostly permanent joints. And most of the places, either it's any kind of products, final products that are available to you, have welding in its prime. For that, we'll little bit have some glimpse of what type of weldings are there, which are mostly used, and the different kinds of welding, and how we produce the welding consumables. So, like, it's not a long one. So we'll take one example, like how we produce the solid wire, and we'll go with that. So let's have some idea of what is welding and what types of welding are there that is available in market. So the very first thing, what is welding? So welding is basically a joining process in which two similar or dissimilar metals are joined either by applying heat up to a certain temperature or by applying pressure with or without filament or flux. Okay. So when we make this kind of welding, it's always a kind of permanent joint. Okay. So when we do the welding, how do we classify like it's done or not? So it's not only like you have joined something and left it. There should be a bond, a metallurgical bond in between them. If between two materials, metallurgical bond are being made with your welding, then the welding is a classified or a, like a well welded. Otherwise, it's fail. So welding is a permanent joint where metallurgical bond is made with the help of application of heat or pressure to join two materials. Likewise, in this image, you can see like two plates are being joined with the help of an electrode, which is creating an arc and joining the material. So this is what is welding. When we proceed further, what types of welding are there? So mostly in the available market, two kinds of welding are there. One is solid state welding, other is fusion welding. So as the name suggests, solid state welding. Solid state welding means the welding will be done, but the material will be mostly into its solid state. Means if you have observed the welding anywhere or if you have seen it, when welding is done, there is molten metal. First we melt the material, then both the metals get mixed with each other, and with time it gets solidified by cooling. But there are other kinds of welding also where material doesn't melt. It only reaches to its plastic state, and then we force it together with external pressure and welding is done. Like in friction stir welding, if you see this very first image, now the material is not in molten state. Only it has been heated through friction to its plastic stage, and pressure is applied. And you can see this extrusion is happening, and with that the metal is getting bonded. So this is solid state welding. The other kind of welding is fusion welding. So what is fusion welding? As the name suggests, fusion will happen. When fusion will happen? Whenever we fuse two things. So in solid form, nothing can be fused properly. So what will happen in that case? The material will first get melted in their molten state. They fuse together, and with time they get cooled and solidify, and then you see a welded material. So in that case, that type of welding, we have gas welding, arc welding, that is readily available in market, you might have seen. Moving ahead, let's talk about little bit about gas welding. So in gas weld, these processes. So in gas welding, what is basically we use gases. What these gases will do? These gases will basically create an arc. These gases will basically create a flame. With the help of that flame, we melt the material and allow it to fuse together. In arc welding, what is happening in arc welding? Basically, with the help of electric current, we generate an arc. That arc will help us in melting the material, and then welding is being done. Similarly, one is resistance welding. What is happening in resistance welding? In resistance welding, we are basically melting the material with the help of resistance. Okay. So that's why it is called resistance welding. The other is solid state welding, like we discussed earlier. The material will remain in its solid form. Only with application of pressure at the plastic stage, the fusion will be done. And this is called solid state welding. So what is gas welding? Gas welding comes under fusion welding, in which the heat is obtained through the combustion of oxygen and a fuel gas. So only fuel gas will not be required. A certain amount of oxygen is also required to burn the fuel. And what will happen when the fuel is burnt? A flame will be made. And that flame will help us in melting the material, either the base material or the filler material. And then on solidifying, it will get fused. So when we come to the gas welding, we have different kind of combinations, like oxyacetylene welding, in which oxygen gas is there and acetylene gas is there. Air acetylene is also there. Oxyhydrogen is also there. Oxyfuel is also there. So these are the combinations with which we make a certain combination in the right proportion, and we make a flame. Moving ahead, in gas welding, the mostly used one is oxyacetylene gas welding. So in this, a combination of oxygen and acetylene gas is used. Then we create a flame in correct proportion. And when the flame is produced, we impinge the flame onto the place where we want to do the welding. That will help us in melting the base material around. And then we use, if required, filler material is also used to fill the gap, and then welding is processed. So the thing is, what are the requirements of gas welding? What the things are required? So if you could see in these images, the gas cylinders are required. In that gas cylinder, what will be there? Like we discussed, two kinds of gas are mostly required. Oxygen is important, or air is important. With one fuel gas is required. So in that fuel gas, we have acetylene with oxygen. So if we'll go in the classification of that, in that case, every cylinder has their own colors. Like when we go for acetylene or any fuel gas combination, then acetylene will have a maroon or red color. Similarly, the oxygen will have a black color. So in this way, we identify the cylinders also. Then a torch is there where you can see through hose, the gases are being sent. At the top, we create a flame, and then welding is processed. Again, while creating this flame, we make a proper proportions to control our required temperature. Like if fuel gas will be more, definitely my flames will be having a higher temperature. So there are different kind of flames: oxidizing flame, reducing flame, neutralizing flame. So this depends on the proportion of gases that we are using. Then you can see these regulators are there, and this pressure gauges are there. These are basically used to control our consumables, like whatever gases we are sending. What other things are required? These hoses are there to carry on the gases. One welding torch is there. Check valve is there. Non-return valve is there. So these are the requirements of gas welding equipments. So what are the advantages? So you can say it's like very primary kind of welding. So earlier days when we were experimenting with the gases and these fuels, that time we have started with it. And the best part of gas welding is portable and versatile process. Like you can carry the cylinders at different locations and you can do the welding. And for controlling the temperature, I told you already, like by controlling the gas pressure and the gas volume at locations, you can control the temperature also. This is good for dissimilar material welding. And also like its cost, it has low cost and maintenance, because if you have seen it, like only gas cylinders are required and one torch is required. So it's comparatively compared to other welding processes, it has low cost and maintenance also. But what are disadvantages? Not suitable for heavy section. Like if you have to weld somewhere at higher place, you can't make a 10, 100 meter and 200-meter long hose pipes. And you're going at going welding at like very critical positions. So that time it will be a little bit difficult to do it. So that's why it's not very good for doing the heavy sections. Then we can control the temperature of flame, but there is a limitation of this flame, that how much more temperature we can go up to, like around 4,000 degrees Celsius or 35,000 degrees Celsius, not more than that. It's very difficult to go up that. So in case if we have to weld a thicker material, we need a high temperature flame or arcs. So in that case, we are going from different welding processes. So for less working temperature, this one is fine. So this is its disadvantage. Like for higher heat thermal input, we can't go with this kind of welding. And slow rate of heating. Definitely when higher peak temperature is low, it will have a slow rate of heating. Then came into history the arc welding. So like we discussed, it is also a kind of fusion welding in which the heat that is required to melt the material is obtained from electric arc. Okay. So what will happen? Basically, we create a kind of cathode and anode situation where voltage drop is there. And when we apply the voltage, the electrons try to come out and an arc is created. And a lot of plasma gas and other things are there. But this, from a general perspective point of view, an arc is created. That arc is having a temperature of around 5,000, 6,000, 10,000 degrees Celsius of temperature. And so, and with that arc, we basically melt the material and then welding is carry over. So there are different kind of arc welding also, like metal arc welding, submerged arc welding, tungsten inert gas arc welding, metal inert gas arc welding, flux core arc welding. So these are the different types in which different like arc, like they are the variants of arc welding. So like I already told that it's using an electric arc to coarsen the metals, melt the metal by use of thermal or heat. And it's a very common welding procedure that is available readily. You can see it everywhere, wherever you go for the welding things. And the same thing, electricity travels from electrode to base material to ground. Moving ahead, what are the components of this arc welding? Like we discussed in gas welding. So definitely if you have to create an arc, you must need a generator or transformer. Okay, so that we call basically a power source. Then we need cables, work electrode to create a cathode and anode kind of situation. Then electrode holder, from where we take an electrode, which will help us in creating an arc. Then electrode itself, which is either consumable or non-consumable. There are different kinds of welding, whether either electrode is consumable or non-consumable. We'll discuss it about it further. Protective shield, definitely. What does it mean by protective shield? Basically, like whenever you are doing welding and when molten material is there, that is on a high temperature. So on high temperature, what happens? The chances of solubility are higher. In that case, the surrounding contaminants get into it, okay, and can create defects. So for that, we need to shield our molten material. For this, we need protective shield, either it's form of gas or in form of slag, whatever it is. Then other things are like the consumables in forms of globes, wire brush, chipping hammer, goggles. These are the protective equipment that requires while doing the welding. What are its advantage and disadvantage compared to the gas welding? So most efficient way to join metals, because definitely having a comparatively high temperature. So in the same time, you can save time and you can save your multi-pass things, and you can do the welding on thicker sections also. Then low cost of joining method, affords lighter weight through better utilization of materials. And since I have told you, like it's one of the more highly progressed and highly dedicated kind of welding. So for all kind of materials that are available in market, the system has been developed and its variants are available. So it is capable of joining most kind of materials. Okay, and having a flexibility in design. Like if you have to do different positions of welding, it is capable of doing it with this one. what are the disadvantages? Like mostly it is manually. Right now, moving towards this automation, but mostly it's a manual welding. And when manual welding is there, then definitely labor cost is higher. Then definitely if we are getting higher temperature, then definitely high energy will be required for it. And apart from energy cost point of view, definitely when high voltage and high current is there, then chance of causing danger is higher. And for disassembly is not convenient, and like defects, chances of having defects are higher. Like I discussed with you, like welding positions. Like there are multiple positions in which we basically do the welding, are like horizontal welding, vertical welding, inclined welding. So there are different classifications like of positions of welding, in which our different processes are there that should be equipped with. Like if I want to do overhead welding, then many processes are there that is not suitable to do it. So in arc welding, they have multiple variants which are capable of doing the multiple positions welding. Like in, if you will see what is 1G horizontal fixed position welding, in which your, if you'll see this is a pipe groove. In pipe, you can see it here, a groove is there in which I have to do the welding. So what will happen? I'll remain my hand straight forward over it and the pipe will roll. So we call it 1G horizontal welding. In other case, my pipe will get vertical. Okay. And I will weld all around. We call it 2G vertical welding. The same way 5G is there, 6G is there. So there are different positions of welding. So when a person go for qualification for a welder, these positioning welding plays a very important role, like the horizontal welding or flat welding. These are easy to be done. So the qualification depends on what kind of weldings you can do. Like a person is qualified of doing 6G welding, he is considered as one of the top kind of welders because he can do welding in inclined position also, overhead position also, round around also. So this basically decides like how much is your qualification. And okay. So, like I told you, like there are variants of welding. So we'll see now because the time permits us a limited one. So we will see one kind of welding and how we are producing its consumables. So let's start with MIG welding, like we have seen it earlier, metal inert gas welding. So what is metal inert gas welding? So as the name suggests, metal inert gas welding. What does it mean? Means a metal will be there. That metal will be in the form of electrode and inert gas will be there for shielding. And with the help of these two, we will be doing the welding. So what it say? It is a welding process in which a continuous solid wire electrode, this is metal, a continuous solid wire electrode is fed through a welding gun and into the weld pool, joining to base materials. So what is there? Like if I have to fill a gap, definitely I need some filler to fill there. So in this case, my electrode, which is used to generate the arc, is the same electrode which is being get consumed while doing the welding. And that is our solid wire. That is a continuously fed wire that is coming through the spool. Arc is created and it is getting melt down, and the same time through the feeder, the wire is continuously getting fed and welding is bit carried out. So what is its key features? Like at high welding speed and productivity, like it's a continuously fed wire. So all the time you not to change the spool or like very frequently your electrodes. So it's a continuously done one. High speed, like it's very handy to learn also and automate also. Like I told you, like the system is moving from manual to automation. So it is one of the most easily automated welding procedure. And it's mostly used in automotive and construction and manufacturing industries. Okay, we'll see further like how MIG is being done and what is method. So if you'll see this video, so this one, the wire, what it is cutting, this is wire, which is continuously getting filled. And you can see the arc is being created. And in this way, welding is being carried out. Okay, let's go ahead. We'll see it in a bit. What is MIG welding? Let's. Yeah. So this is our solid wire that is coming, and this is our spool. Okay, from here the wire is continuously fed ahead. You can see this way, the wire is coming out. Okay, the arc is being created and it is getting melt. When arc will be created, definitely it will get hot, it get melt, and the wire is continuously being fed. So arc will it will visualize like arc is continuously ignited, and the water and the metal droplet is coming and filling the gap. This way, this MIG building is being carried out. In this one, you can say much better way. Yeah. You can see in the top one how it is being getting filled, and you can see the how the arcing is there. So this way, this is continuously getting filled. Yeah. Okay. Fine. So this is this regulator is there for shielding gas. You can see, yeah. Shielding gas is required for shielding the molten metal because it is hot, it is in liquid state, so chances of having higher solubility, so the chances of having contaminants is higher. So to seal that, we use a shielding gas at back. Okay, let's move ahead. Yeah. So likewise, we have seen metal and gas welding. One more variant is there. We call it submerged arc welding. Okay. Again, if there is some name, there is some meaning of it. If submerged arc welding, it means the arc will be submerged somewhere. So where it will be submerged? It will be submerged under a flux. So what flux will do? Likewise, we have gas for shielding. In submerged arc welding, we have flux for shielding the arc at place of gas. So what is that? In this one, it's an automatic and semi-automatic welding process in which arc is struck. How arc is struck? The same way a filler wire is there. Solid wire is there, which is getting fed through continuously through. Okay, and arc is created. But there, what in MIG, what was happening? The arc was created and a shielding gas was there, which was shielding it. Here, it will be submerged under a flux. You can see it here. We call it flux. They are specially designed consumables for different grades of material. So arc will remain inside it and it will seal the molten material. What will happen? So you will say like, sir, but this can create a contaminant. No, but this flux is designed such a way that once this molten metal will get solidify, this flux will having a comparatively lower density than the molten material. So it will come to the surface and we can chip it out. Okay. And so you can see this video. Now here, the arc is there submerged inside, it's happening, it's doing the welding. And from there, you can see the flux is being poured ahead of it. Arc is there inside. Okay. This way, the slag will be formed. And after completing the weld, we can chip it out. In this welding, in this video, you can see it better. This way. So what is happening? This is our electrode or wire, which is continuously fed one. So it will create a arc. At the same time, you can see flux is there that is coming from the super. The arc will be created and the flux will cover the arc and it will get shielded. This way, the welding is carried out. Yes. So once the arc is inserted, either we can start pouring the flux ahead of it or immediately when it started the arc. And this way we can do the welding. So again, it has its components like hooper is there. Okay. This is the welding torch. Okay. This is the wire feeder or this is the spool of it. This is the controller. So these all things are required for doing the welding. like we have discussed many times, how we do the welding, how the solid wire, this electrode is helping us creating the arc, and then it is getting consumed also, getting into the groups and making the welding. So how we basically make this electrodes? So like I have discussed with you, two kind of welding process here. One is MIG welding, the other is saw welding. In MIG welding and saw welding, in both we basically use solid wire. Okay, continuously fed solid wire. So we'll see like how we prepare this solid wire. Okay, so I'll just give a simple process chart. So as the name suggests, it's a solid wire. So solid wire means definitely it will be a cylindrical wire kind of form. So we get a coil of having a diameter of around 4 or 5 mm, and then we reduce it up to a certain dia, how much we require, and with certain stage of production. The very first one is the coil is passed through a wire brusher, where what will happen, whatever skill is there on the incoming coil, that can be get cleaned. Then we come for the first stage of wire drawing. What will happen in first stage of wire drawing? The first stage of wire drawing will draw up to a certain diameter. Then comes the second stage. We give some time from, likely if I want to have that you can say the reduction ratio. These all things matter. What is going to the fate of the final product? So we give it in the two stage. So first stage of wire drawing, the second stage of wire drawing. What is happening in wire drawing? In wire drawing, we have solid lubricants. Okay, we'll see it further how it happens. Okay, so through that we pass the wire and then it go ahead and then the drawing is been done. Then what we do? We bring it to a wire wiping unit. Whatever lubricant is there stick to the surface, we wipe it through the help of wire wiping setup. Then we pass it through a hot wire where all the lubricants or whatever there is on the surface of the wire that can be get cleaned. Then we bring it for pickling. Like if some contaminants or like some kind of oxides are there on the surface of our wire, that can be get cleaned with the help of pickling. Okay. Then after pickling, what we do? We do the coating. Why coating is required? Because if a normal wire is there, like if a bare wire is there, what will happen? If a mild steel or carbon steel wire is there, and if it's not getting coated, definitely with time it will get rusted. To avoid this rusting, we basically do the copper coating. Okay, so that it can be preserved for a longer time. And what is especially in that? What else is the, like you can say, what are the other benefits of this copper coating? Is like, definitely we know that the copper has better emissivity compared, not emissivity, like this electron emissivity compared to iron. So when copper coating is there, electron emission will be easy. When electron emission will be easy, arc generation will be easy. So it helps us in this regard also. Okay. After copper coating, what we do on the wire, we basically pass it again through a normal water because we have passed it through acid pickling in copper bath. Okay. Then we neutralize it. So for that, we do it normal water washing for neutralizing. Now again, my wire is still wet. So I pass it through induction heater. Okay. To get it dry. And then we do the final size reduction. How much we want to bring. Like if I want 1.2, I'll bring it to 1.2. And then we do the bobbin packing. So this is general flow chart. We'll see it in a detailed form in the next slides. But before that, let's see what is wire drawing. So if you see these videos, what happens in wire drawing? We have different set of dies, okay? Reducing in size, stage by stage, through which we pass our wire and getting it reduced to reduce this friction and to produce this weird thing. We use lubricants in between. It can be wet or dry both, okay? So if you see it, there are 3 dies, okay, with reducing in size in between them, okay? And so if you see it, we have a raw material, okay? With time, when it will pass through the dies, each size is getting reduced, okay? And last the puller will pull the wire. So this way we do the reduction. So this is my initial wire. when it pass through a dies, its size get reduced. When it pass through another die, its size again get reduced, and this way we do the wire drawing. You can say the same thing in this video. Okay. You'll see how the wire drawing is over at our place. That will show you through this animation video. Yes. So wire. What is it? After removing of the iron oxide layer through either through descaling, either through wire brushing, what we do? So, like I said you before, passing it through die, we use some lubricant. So here we use solid lubricants. Okay. So this is our primary coil. It passed through lubricant and then it passed through a die, and the die got reduced. So, like if I have reduced from 5.5 to 2, I go in certain stages like 5.5 to 4.5, then 4, then 3.67, then 3.2, and this way we reduce it to 2. So this is the main stage of wire drawing. So this I have shown. Now we'll see all the equipments of this solid wire production step by step, and we'll try to understand it. So what is the very first thing? This is the coil that we got, that we get in start. Okay, like from any of the industry, either it's Sandal coil, start or wherever, whatever grade we require, we order it and we get it in the form of coils. Okay, then what will happen? From this coil, we take the wire. Okay, and here this is the back side. From front side, it looks like this. It has descaling unit. So what will happen? The wire will pass through these descalers. Okay, and whatever scales are there on the surface of wire will get removed. Okay. After this, the wire passes through the wire brusher. So if you see it, the wire is passing through here, and this metal brusher kind of thing is there. So when wire will be passing from here, this will start rotating. And when the wire will pass through and come in conductivities, whatever there is on the surface of wire will get removed. After this wire brusher, it passes through the first stage of drawing, basically the drawing process. So the same I have shown you in video. These drums are there, this die box is there. Okay, something like this. This is the die box where here inside there is die and there is the lubricant container. The wire is passing through here, through lubricant, through die, and go to the other drums. So this way we reduce our wire at every stage. Okay, once this primary drawing is done, it is bring to the secondary drawing. This is the secondary drawing. It is same as a primary drawing, but it does in 2 stages. After when it is passed through it and we have used lubricant, so there must be something stick to the surface, because definitely it is passing through in between. Some lubricants will get a stick to over it. Okay, heat generation is there, so chance of sticking is high. After it, we pass it through this brusher unit. Okay, in brusher unit there is nothing. A scrubs kind of thing is there. The wire is passing over here and it will keep scrubbing it. Then what we do? We pass it through hot water cleaning. From here, the wire will be passed and there is hot water inside. When water is passed through it, after scrubbing, whatever there on the surface of wire will get removed. But now what happened? Only the thing that has been attached to the wire from the top or from the external source, like the lubricants, other things, those things only get removed. Okay, but something which is already inherent to the wire, like some oxides or some on the surface, that will not get removed through the help of this hot water cleaning or like this descaling. So that's why what we do this acid pickling. Definitely what we do acid pickling is like acid is there. So definitely when acid is there, some reactions will happen over it. So the oxide layer will break with the help of this acid, and the water and through the wire, we remove the oxides layer over it. Because before doing the coating, we need to have a clean wire. So for that, we do the acid pickling. Then after acid pickling, we bring it to copper coating tank. What happens in copper coating tank? With the help of electroplating or with dip coating, the coating is being done, in which we use a combination of copper sulfate with some amount of acid and some amount of water. After coating, as I told you, because already we have done with the help of acid, definitely my wire could have got acidic or some acid on the surface of it. And definitely if acid will remain on the surface of any material, or any metal, especially ferrous material, then chances of getting corrosion is higher. And why we are doing the copper coating? To reduce the chances of corrosion. So after doing this copper coating, we need to neutralize it. For this neutralization, we pass it through the water washing. Okay, those water washing is done at the room temperature only. Now my wire is passed to the water washing. So definitely now acid might not be there, but water is there. So prior going ahead, what we do, we pass it through induction oven. Okay, through this induction oven, what happens? My wire will get dry, and then I go for a final size reduction, and this way we pack it in a bobbin. Okay, so this is the whole method of making the solid wire, or like the wire for MIG and SAW welding. Thank you all. I think time's over also. Now we have 5 minutes to close. So if you have any query, any kind of question, we can take it from here. Yeah, Dr. Ipsha, if you are there, we can proceed from here.
Participants, if you have any questions, you can unmute yourself and ask. Participants, you can ask in the chat box also. Sir, one question is there. Have you any idea on how can AI
AI-driven predictive modeling optimize welding parameters?
methods to minimize defects and enhance weld quality in advanced steels like carbide field magnetic
Great.
steels?
It's a nice question. The thing is, like for any AI-driven predictive modeling, we need a set of data points. Okay, so that's the most important one. To create any model, the data thing is the most important, and the link data one. Starting from the RM until the FG, like the finished good is consumed with welding, with the application, then definitely we can do it. Undoubtedly, if like nowadays people are already doing it, like for the identification of defects or the for minimization of defects. See, like if some defects are coming from the composition of RM, okay, and you have a data points like in certain RM composition you are not getting those defects, and other there are defects, and in that way you can definitely make a predictive modeling. But the thing is, you need that set of data points to create a model. It can be done. And AI has made it possible that you have if you have a capability of making algorithm, you have a capability of setting the data sets at the right aspects with the right parameters. Definitely you can do it. People are already doing it. Now the things are moving towards the models only. So it's a good one. We can do it. I don't think like it can't be done. Any other question from anyone? If you really want to have some project over this, get connected with some of the, basically you can't get this much of data from any of the institutes. Definitely you need to come in contact with any of the industry who work in this field. Okay. And definitely they must be having a test for their RMs, their FGs. Okay. From them, you can collect the data and you can process for your model. Another question, what methodological strategies and welding process parameters can be optimized to minimize the formation of metal phase in a heat affected zone? From metallurgical strategies and welding process point of view. See, the thing is, if I'll tell you very clearly, if you'll go for laser welding, okay, and they go from just a simple point of view, you go from a laser welding point of view, and you go from a arc welding point of view. Definitely the chances of having a thinner heat affected zone is more in laser welding and thicker in arc welding. Okay, so the heat input plays one of the major role, as well as the size of the heat affected zone. Okay, in that case, those parameters, like deciding a parameter doesn't mean only like you're seeing from this point of, or from a single aspect point of view only. Other things are also there. So a optimized one is required, and that optimized depends on what exactly you require. So if you'll ask me from building process parameters from a point of view, then definitely heat affected zone depends on the height, the peak temperature and the heat input. From metallurgical strategies point of view, then definitely the kind of RM you have, the composition of RM you have, that plays a major role. But these two questions are really very good questions. I appreciate the people are listening. Very good one.
Any more questions from participants?
If you have further any question, you can write to ma'am, and ma'am can forward it to me or Suresh sir. I will definitely reply back to you. Ma'am, I think it's already 16:01. So is time up, or like we have to continue more?
No, actually up to 6:30 the
Oh,
session
fine.
is there.
Then we can start. I thought like it's up to 6 only.
Okay.
Then we can
No,
go
at
for more also.
6:30. At 6:30 the session will end. Then the participants will have their online exam at 6:30.
Okay. I thought like that's so I went very fast. Otherwise, I would have gone slow. I would go in more detail in the every slides. I thought like it's up to 6 only. I'm not aware of it. Sorry. Okay. Anything else? See. Okay, then let's interact with the people. So we discussed basically two things over here. One is the material. Okay, what kind of steels are there, and what those are available in market, and from which aspect the industry is looking into it, their nomenclatures and other things. And the second thing what we look into and what we saw was welding. Okay, so welding is a general topic. We might have studied in our courses also. I'm coming to like I am from an industry. We can deal with anything. But the thing is, if you want to come up something with this process point of view, and if you have some questions on this processing or the production process, then we go to discuss again, not an issue.
Okay, sir. Then we can conclude this session if as participants have no more questions.
Okay.
Sir, it was very beautiful lecture on welding, starting from the materials to how we join the materials and the processes of welding. Everything you have explained very nicely. So it was very beautiful learning the participants can get. Thank you.
Thank you, Dr. It was a good opportunity for us also to interact with you guys. And I really appreciate these two questions. Undoubtedly, like these are very good questions, very beautiful questions for this coming insights. Like one is on AI, and the other one is like particularly someone is asking about heat affected zone. So very definitely the persons will have a. It means like your team is really doing good in welding. I could say it from metallurgical point of view also. One is from metallurgical point of view, and the second one is from advancement, like AI driven predictive modeling. These two are, one is from physical or like practical aspect, other is from modeling aspect. Definitely. Good luck for your futures, all of you. Thank you.
Thank you,
ma'am.
sir. Thank you,
Thank
sir.
you.
So participants at 6:30, you can log into your individual IDs for the exam. It will start at 6:30 and it will be of 30 minutes duration. After the exam, we will have a valedictory session. It will be the concluding of this activity. Okay.
Ma'am, can we leave now?
Amulya,
Hello. Ma'am, can we leave now and rejoin for valedictory?
Yes, yes, no problem.
Okay, sir. Thank you.